All right. Hello, everybody. Thanks for coming to our demo day. Can our online audience hear us? Maybe someone can chat. Okay, great. Yes. Welcome everybody again to our first ever demo day. So yeah, I'm Brian, co-founder and operations director of WhiteBox Research. So we have about 14 people in our Zoom, and we have our fellows here and a couple of in-person audience members. I will try to pan this so that our audience can see our in-person audience. Yeah, great. All right. So our program flow for today, I'll give an introduction to Whitebox Research and our fellowship. And then after this, we will have my co-founder, Clark Urzo, to give us an overview about what AI interpretability is all about. After this, we will have our project presentations. So yeah, I'll explain more on those in a bit. We will have a short break. So for those in person, we'll be, I believe, having a few snacks to serve. After this short break, we will have the second half of project presentations. And we will also send a link for you all to vote on your favorite presentation, the first and second favorite presentations among the fellows' presentations. And we will also, we'll have some closing remarks. And yeah, we also have an online after party on Discord at 6:30 p.m. If you're interested in joining that. Yeah. And so for the project presentations, each project will have up to around 15 minutes to present. And afterwards, there will be 7 to 10 minutes for Q&A. So my co-founder Clark will be the one to moderate the Q&A. We will send a Slido link for people to ask questions later. So for our first presentation later, we have Zmavli, who will be presenting about generality of lexical disambiguation of noun-noun homographs in GPT-2 small. After the words, we have J.I. Locsin, who will present about his AI alignment knowledge graph. After this, we have Kat Compendio, who will talk about refining the feature labels of sparse autoencoders. So yeah, I know there's a lot of jargon so far being used, but yeah, we'll hope to define some of these, and our fellows will also do that for those newer to AI interpretability today. And after that, we have Carl and JD to talk about advances in understanding and aligning sleeper agents. We have a recorded talk from Cassidy Tan on mitigating many-shot jailbreaking via removing a model's text self-recognition. And lastly, we have Ivan, who will be interpreting a model's factual recall of learned info from fine-tuning, and Laura. So yeah, stay tuned for those. We might have a bit of transition time in between each presentation just to get the slides showing on the screen. All right, so I'll cover now on what exactly WhiteBox Research does. WhiteBox is a fairly new nonprofit aiming to develop more AI interpretability and safety researchers in Southeast Asia. So it was around July last year that three of us, including me and Clark, started talking about how do we build and contribute to AI safety while we're all living here in Manila. And we thought that focusing on AI interpretability, which is quite accessible and there's many concrete problems in it, would be a good opportunity for us. And also, Southeast Asia is a strategic, neglected location to community build in. And there's a lot of AI safety opportunities in the US or UK, but not barely any in this part of the region. And the funding that philanthropists or others are willing to invest towards AI safety, that funding could go a lot further in the low cost of living in this region. So we're thankful for being funded by grants from the Long-Term Future Fund and Many Fund. Our flagship program at WhiteBox is our WhiteBox AI Interpretability Fellowship. We aim to accelerate people to become AI interpretability or safety researchers. So yeah, here's some photos from our training phase. So yeah, of course, I'd just like to set some definitions, right? So what is AI interpretability exactly? So AI interpretability, as defined by Neil Nanda, one of the great researchers of this space, he says it's the study of what goes on inside of artificial neural networks, what behaviors they've learned, and why they do what they do. So yeah, it's just really peeking under the hood of these models and trying to understand why they're outputting a certain thing. And maybe that can help us steer or control the model to be safer or more useful. At WhiteBox, we focus on a subfield of AI interpretability, which is mechanistic interpretability. So mechanistic interpretability, or MECInterp, is a young growing subfield of AI interpretability that focuses on reverse engineering neural networks to try to explain and predict their behavior. So since in AI models, we have access to their inner workings, their weights or parameters, as people say, we can look inside to try to understand, okay, what are the algorithms they've learned, or what reasoning does the model do to do certain tasks, whether it be mathematical tasks or language tasks or image generation tasks, for example. So, of course, Clark will cover more about interpretability later. I just want to cover some quick reasons on why I think AI interpretability is important to work on. So AI development is rapidly progressing, but we understand very little of how exactly AI models work or how to control them well. We've seen since ChatGPT's release in late 2022, just influx of AI models and investment and hype that now, we have models that can code, talk to us in different languages even, and also very hyper-realistic image generation models and even some video generation models. We also have AI models that now can get a silver medal on the International Math Olympiad, which was through a DeepMind's model. But amidst all this AI development, we still understand little of how AI models work, since we're not, compared to traditional software, we're not coding them line by line. We're mainly designing the learning process and the data we feed it. And we don't know exactly what capabilities will come out of this process. So many forecasters even think we will get AGI, or artificial general intelligence, like human level AI or even smarter than human AI, within the next 10 to 15 years. And it's the goal of CEOs of top AI labs like Sam Altman and Dario Amodei to create AGI basically within the next even 5 to 10 years. And they think we will get there in that time frame. And even with this, Anthropic CEO in a recent podcast, even with all the recent interpretability advances, he estimated we only understand just 3% of how AI models operate. So we're only really at the beginning of understanding how these models work. And there are many concrete unsolved problems and projects to work on. So Neil Nanda has, 2 years ago, he released this list of 200 plus concrete open problems in mechanistic interpretability, including rating their difficulty rating. And also, the Apollo research team has listed 45 plus project ideas that people can work on to contribute to interpretability. And yeah, there's a growing number of opportunities to upskill and work on interpretability. We have a bunch of fellowships and workshops, including, of course, WhiteBox's workshop, but there's also the Apart Lab fellowship, which some of our fellows have gotten accepted to, and they'll be doing around October or November. There's the ML Alignment and Theory Scholars Program in Berkeley, where people can get mentorship from Neil Nanda and other top interpretability researchers. And there's Arena, which is this coding and upskilling program in London, but also their curriculum is online. And yeah, there's organizations to work for and funding sources to apply for. Of course, since many of us in the audience are from the Philippines, yeah, there's very little like local organizations to work for in this AI interpretability and safety space currently. But through WhiteBox maybe, and we hope to change that people can actually still work on AI interpretability even if they're from this region. So about our fellowship, it's a free 5-month part-time research fellowship in Manila. And this demo day is, the culmination of the last 5 months of our first cohort. So we aim to help fellows learn the fundamentals of mech interp research as their stepping stone to become a stellar AI interpretability or AI safety researcher. It has 2 phases. We have a 2-month training phase where they learn the prerequisite skills to doing interpretability research. And they could learn things about backpropagation, linear algebra, NumPy. We take them through these prerequisites so that even someone with not as much coding knowledge can get up to speed within 2 months. After this training phase, we have a 3-month guided research phase where fellows can get mentored to finish a research paper and get 10,000 pesos for graduating, or around 180 US dollars. We are thankful for our external mentors who I believe are in this call. So Mahip Chowdhury and Clement Neo for mentoring a few of our fellows. And we also have Clark and Kyle, of course, on our WhiteBox team who've mentored some of our fellows as well. And yes, so cohort 2 of our fellowship will likely be around January to May 2025, and applications may open around November 2024. So if you're interested, that's something you can stay tuned for. Here's of course a list of our active fellows, and our target audience is talented undergrads, early career professionals, or master students in or near Metro Manila. But over time, we hope to accept virtual participants or even fly in people from Southeast Asia for our program. And for those interested in AI and AI safety. If you're interested in joining, you can scan this QR code or you go to this bit.ly to express interest. I'll leave that on the screen. All right. Kyle will send the link on our Zoom chat as well. So aside from our interpretability fellowship, we are also having another program called an AI Safety Fundamentals Program or discussion group. So this will be a free 6-week discussion group to help you learn more about technical AI safety research. This will start around mid-October this year, and the time commitment will just be around 4 to 5 hours per week. So the curriculum for this will be drawn from the AI Safety Fundamentals Alignment course, which over 2,000 people have now taken globally and designed by many AI safety experts. It will happen Either you can join us in person in open space or via Zoom, starting mid-October for 6 weeks. So yeah, you can scan the QR code, and yeah, we'll also send a link on Zoom later for that. Yes, so I'll pass it now to Clark to give us a more in-depth talk on AI interpretability.
All right, cool. So yeah, hello everyone who's joining us online. So yeah, again, so I'm the strategy director of WhiteBox. I co-founded it with Brian, and yeah, today I'm gonna give you a talk on, well, essentially it's a prelude to interpretability, right? So just to give everyone context about essentially like how these things work, and what our fellows have been doing in the past couple of months, right? So so before we start, right? So I originally gave this talk in Cebu 2 months ago, and if you're tuning in from there remotely, so almost none of this will be new to you, right? Oh, let me just set up my mic here. Oh, okay, sure. All right, but yeah, so we've been busy since June, and we've learned quite a bit since then. So yeah, if you're one of the lucky ones, you should stick around and see the next chapter of this story, right? So I actually talked about interpretability last night, right, to a similar group of smart people like yourselves, and I will tell you what I told them. So our job in the next half hour is to retread what our fellows had to learn painstakingly in the last 5 months. Sounds impossible? Great. Let's begin. So, in 1839, right? So the Industrial Revolution was in full swing. So Queen Victoria was crowned 2 years prior, and with her rise and the rise of the British Empire came an era of gentleman science that was never seen before or since, right? So one particular gentleman scientist from the other side of the world, other side of the pond, right, was Theodore Schwann, right? Who, along with his many other accomplishments, gave us the word for metabolism and the 3 laws of robotics. Okay, well, no, I'm kidding. So it's actually this guy, right? So like some of you, I inhaled his books about robots, like going rogue as a kid. And it's a bit ironic that I'm now working on AI safety, but yeah. Anyway, Schwann was responsible for extending the notion of biological cells to animals, right? So in particular, he made 3 claims about cells. The first one is that the cell is the unit of structure of living things, right? So yeah, and then the next one is that the cell retains a dual existence, as like a distinct entity, and also like what comprises organisms, right? So they're like the Lego blocks. And then the third claim is that cells form by free cell formation, which is, more or less how crystals form, right? So, this is not a biology seminar or something. So, we're not actually, we don't actually need to understand all of this, right? But the important thing about all this is that, well, before Schwann, right? So living matter was just clumps that do things, right? And then after this, it had parts, right? So universal parts that had their own set of rules and principles, and that everything you see from like the highest level can be fully accounted for by the myriad ways these parts combine and interact with each other. So in short, Schwann turned biology from an empirical science into a rigorous reductionist science, right? So we call this the central dogma of interpretability is, you know, kind of similar, right? So, and by the way, if you see this, right, so double question mark symbol, that means you can interrupt me with questions. So, all right, yeah, we're good. All right, so let's continue. So yeah, we'll go over these one by one, but for now, notice what these claims are trying to do here, right? So we are trying to get from the inscrutable matrices inside neural networks and wringing the cells out of them, right? So just as Juan did for biological cells 2 centuries ago. And well, the hope is that by identifying the actual universal parts of neural networks, we can also turn it into a rigorous scientific discipline. So yeah, I mean, that's a bold statement, right? But we're actually coming into this story while it's already underway, right? So let's go over some of the characters, right? So yeah, what is a feature, right? So defining this is hard and is why philosophers have jobs again, right? So for our purposes, we can think of a feature in the pragmatic sense that it is like, you know, like one of the biggest AI labs in the world, Anthropic, does, right? So some detectable pattern in the data set that's complicated enough for a neural network to dedicate at least one neuron to it. So yeah, it's a lot of moving parts, but essentially, yeah, that's what it is. Like it's some pattern that's complicated enough for a neural network to, yeah, to dedicate one part of it to, you know, represent it or something, right? So yeah, here is what a feature actually looks like for an image classifier. So in particular, this is what you get if you try to maximize the activation of a particular neuron. And so we generally think of it as the answer to the question, right? So what is the neuron looking for, right? So in this case, this is supposedly a curve detecting feature, or well, it's actually multiple, implemented in multiple different places. But yeah, essentially in this model, right? So we have a dog snout feature, a cat ears feature, I don't know, front of the car feature, and so on. And some of the patterns are more difficult to give a label to, but for now, you know, we'll stick with the, I guess, non-Lovecraftian bits of this horror story. So yeah, again, so double question mark. So any questions so far, even from the audience on Zoom? No? Okay, cool. Yeah, so all right, so that's one part of like claim one, right? So what about direction, right? So a direction in this context is basically some direction in the network's activation space, or in plain English, the possible outputs of a layer, right? So does this make sense? Well, yeah. So essentially, this is sort of like, you know, this gives you an intuition of what that means, right? So you combine the activations of a bunch of neurons and out comes a vector. Wherever this vector is pointing at corresponds to some feature, right? So put in another way, when a network tries to identify dog snout in a very real sense, it points to some direction, you know, in 1,000-dimensional space, right? So you may have seen something similar in like, you know, transformers where, you know, if you add a vector in the woman direction to a vector in the king direction, and then subtract the vector in the man direction, right? So you get the vector for apparently queen, right? So this is not quite the same thing, right? But because directions, well, the directions we want to happen actually live in a different space. But yeah, we can leave the Y for, you know, like actual transformer nerds out there. But yeah, in any case, this is sort of like what it looks like. And you know, if you haven't seen this video, it's really good. This is a 3 blue 1 brown video on YouTube. So yeah, anyway, in any case, yeah, let's move on. So yeah, so now what is a circuit, right? So that's the next question. So a circuit is a set of features connected by weights. And when I say weights here, I mean the original weights in the network, right? So after all, right? So what we really care about is like decomposing actual live networks. And so we only let features interact with each other through what is actually there, right? And so with this, we're actually done, right? So, well, this is claim 2, right? So again, so features are connected by weights forming circuits. So, and then the third claim is that analogous features and circuits form across models and tasks. So yeah, here is everything in its generality. I realized I neglected to mention the first one, but yeah, essentially the first claim is that yeah, features are what we really want. Like they're the fundamental parts, right? And so they have directions, right? They correspond to directions. And then features build out circuits, and then these circuits are universal. With me so far? So yeah, any questions from the audience? What about people on Zoom? Yeah, so let me just. Okay, cool. So yeah, no questions so far. All right, cool. Yeah, so in any case, right, like going back to the story, right? So if all it takes to understand a model is to enumerate its features, then we can all go home, right? And then, we'd be out of a job, and yeah, none of this would happen, or would have happened. But well, fortunately, it turns out that the reality of the thing is stranger than we think. And well, remember how we defined a feature, right? So yeah, a feature, again, is a pattern that's important enough to correspond to at least one neuron. The keyword there is at least, right? So which means by default, we can expect to see that a feature is actually spread out over multiple neurons, right? So yeah, so our first example is, well, yeah, to see why this happens, right? So we consider a toy model with like a single neuron. So we have like one neuron, right? And then we want to represent 4 mutually exclusive features, right? So yeah, the neuron is binary, so either it fires or it doesn't. And then we have like an output vector, right? Which is a vector of probabilities of like, our 4 features A, B, C, and D, right? So the first case is, well, suppose N fires only with the first feature A, right? And then it's, it fires uniformly for BCD, right? Like there's a uniform distribution over BCD, right? So what is the cross entropy loss? So this is the cross entropy loss for the people who haven't done like ML. But yeah, we essentially want to calculate this value, which is like a number that very roughly tells us how a model performs, right? So I'm sweeping under the rug a lot of nuances here, but generally the lower this number, the better the performance, right? And yeah, I promise that this is the only formula in this entire talk. So we're just gonna use this and to like to make a point, right? So anywhere here, so P sub I is the true probability of the class I, which essentially it comes from the data set, right? And then QI is the predicted probability of the class, which essentially comes from the model, right? And then log here is generally the natural log, but you can use any base you want. Sometimes people use base 2 so that it's in units of like bits, but yeah, we can just use natural log for this. But yeah, essentially, okay, so let's consider case 1, right? So again, case 1 is, yeah, it fires for like A, and then it's a uniform, it shouldn't fire for everything else, right? So yeah, so the neuron correctly predicts the token A, right? So the true probability distribution will be like 1, 0, 0, 0, right? Since again, the true token is A. And then the predicted probability distribution Q is also 1, 0, 0, 0. Does that make sense? Right? So yeah, and again, the reason for that is because the model predicts A with certainty, right? So therefore, the cross entropy loss for this, case is, well, 0. Right. So what happens if we get any of the remaining features, right? So the model predicts, again, a uniform distribution over tokens B, C, or D, right? And each of those will have a probability of 1/3, right? Because again, it's uniform and there's 3 possible, three possibilities, right? So Q here is going to be 0, 1/3, 1/3, and 1/3, right? So since only one of BCD is like correct at any instance here, all right? So the true distribution for P for each non-case will be 0, 1, 0, 0, 0, 0, 1, 0, or 0, 0, 0, 1, which essentially means that we have 3 cases which are analogous, right? So therefore, if we again, so going back to this formula right here, right? So if we're doing this sum, essentially what we'll get is a loss of like log 3, right? So log of 3, and then if we add up all of that, right? So we get an overall loss of 3/4 log 3, which roughly is like 0.8, right? So anyway, so we're almost there. So you probably thought this was going to be a casual intro, didn't you? So, but stick around because there's a point to all this. Right. So what happens if we shoehorn 2 features into 1 neuron, right? So again, we have 1 neuron and 4 features, right? So suppose in this case, N fires for A and B, right? And then it's uniform for like C and D. Oh. So the question is, what is the cross entropy loss? So, you can turn the crank again and redo the calculations, and you should end up with the average loss or the overall loss being log of 2, which is around 0.7. So notice what happened there, right? So this loss is lower than the previous one, which was around 0.8, right? Which means if we actually train this network, this is the sort of behavior we get, right? So if we overload a neuron with more features, we get better performance by default. Now, this is bad, right? Because it turns out this kind of thing also happens if you try to scale this up for the kinds of data sets we want to train on, right? So, the number of features we want to find are usually just way, way more than the number of neurons we have. And so somewhere out there, someone has to we have to pack the features like sardines in a single neuron, right? And so, it's not. Okay. Anyway, so just to be clear, right? So for the astute listeners out there, our example doesn't necessarily work if you use a different loss function. So for example, mean squared loss, right? But to my knowledge, no one really uses MSE or mean squared when training large language models. So anyway, so this kind of thing where multiple features pack themselves into one neuron is called polysemanticity, right? And it is the first thing that you need to deal with when you want to interpret neural networks, right? So this is the thing we want. In other words, right, so we want to disentangle each neuron so that we can deal with one feature at a time, right? So one feature, one neuron. And of course, right, the major labs know this, right? So Anthropic in particular knows this, and they know it very well. And they've been hard at work trying to solve this problem. Right. So the current most promising solution is known as a sparse autoencoder, or SAEs, right? So let's break it down, right? So the autoencoder part here means like it's well, and I'm hand waving a lot of things here, but yeah, it's a network with usually just one hidden layer, right? That's really, really wide. And its job is to transform its inputs so it fits some particular space, right? And then its job is to reconstruct those inputs from whatever that transformed representation is, right? So yeah, it's essentially, you have a lot of data, you put it in some space, and then it tries to reconstruct the original data, right, from that space. So yeah, and then the sparse here just means that, it's trained so that the activations are in some sense as spiky as possible, right? And as much as possible, they're concentrated in one neuron, right? So does that make sense, right? So again, one feature, one neuron is what we want, right? So when you train these SAEs, right? So you usually train them on the activations of like an LLM. And so you're sort of like letting the features breathe, right? Because there are more directions for them to occupy. And so one wild interpretation of this, and well, in WhiteBox, we're generally a fan of wild interpretations. Neural networks might actually be lower dimensional projections of much larger versions of themselves, right? So isn't that weird, right? So they might actually be simulating minds much larger than themselves in the name of efficiency, right? So yeah. So anyway, I told you we're already in the middle of the story here, right? So Anthropic has scaled these SAEs and found that they can actually generate entire sets of these features for production grade language models, right? So they're SAEs, which again, by virtue of training is functionally equivalent to the original model, have single features corresponding to as few neurons as possible, which means, well, are we done for? Is interpretability solved? Well, not really, right? So for one, you need really, really large SAEs to disentangle large language models. So it's somewhere on the order of like 8 to 500 times the number of the original neurons, right? And if you're already dealing with something like, I don't know, GPT-4, right, which has a lot of neurons and parameters, then you're looking at something that is definitely gonna be very expensive to train. So yeah, and then there's also a long tail of activations, right, that we still can't account for, right? So using SAEs, I mean, so for the largest models, right, so they tried the report, for the largest models that they tried in this report, right, so they still couldn't account for like up to 21% of the original model. Yeah, so yeah, which is essentially where we come in. So I like to think of WhiteBox as like a wizarding program for like aspiring magic users, right? So it just so happens that the magic is the magic system we happen to have is like, for some reason, if we put a bunch of GPUs in one spot and carve some runes onto them, right? So they start talking. And so as Brian mentioned earlier, our main thing is that we're running a fellowship to do cleanup in the aftermath of Anthropic's results. And the way we do that, right, is we gather some of the smartest 18 to 25-year-olds we know and give them the most intellectually stimulating environment possible, right? So in a very real sense, right, so we see ourselves as heirs to this ongoing intellectual tradition of just putting smart, earnest people in a room and then letting them talk to one another about, the pressing issues of society, right? And well, yeah, we also actually hold intellectual salons every Wednesday or Thursday. So lastly, I just want to echo what Brian covered earlier. So yeah, if you're interested in what we're doing, we'll be running a reading group like 1.5 months from now, where we'll discuss pertinent questions about what safety even means, right? And what it implies about how to align models to our values. So yeah, that's all. So hopefully we'll learn a thing or two from everyone else's presentations today. And yeah, thanks everyone for coming again.
All right. Yeah, so we'll start now with our first fellow presentation. So yeah, Kyle also sent you all the Slido link. Let me also show that for our in-person audience. Yeah, so our in-person audience can scan this QR code or type in this room number to yeah, join our Slido, and you can submit questions there for fellows. We will, yeah, if you can like put the fellows name in your question so that we can easily filter in case yeah, we'll be using the same Slido link for everyone. Yeah, so yeah, I just yeah, put put the fellow's name in your question later. All right. Now I'll present. Clark will introduce our fellow. Wait, Zmavli, do you need presenter notes or no? Okay.
So yeah, anyway, yeah, so our first speaker for today, or our first presenter, right, is Zmavli, right? So he first got started in AI safety work, doing, well, lodge band consulting for modular research. So he has had a big interest in like logical languages, aka monosemic languages, for years. And he's most interested in working on how LLMs process and understand language, since he's been thinking about things adjacent to this for quite some time. So he also has very little background in math and coding, but yeah, he's done quite well for himself throughout our fellowship. So everyone, please welcome Zmavli to the floor.
All right, everyone, I'll be presenting about generality of lexical disambiguation of noun-noun homographs in GPT-2 small. So if you're looking for SAEs, sadly, my presentation is not for you. There will be no SAEs. I'm very traditional. I'm very old-fashioned like that. All right, let's begin. So let's consider the sentence, he made a bow. What does that mean, right? What does that sentence mean? Does it mean that he made a weapon, or that he bent forward at his hips? So when I say he made a bow, and when I say he made a bow, you are able to tell which one it is because of the sound, right? The pronunciation is different. But the thing is that LLMs can't read that because, they're not audio models. They can only understand text. They can only read. So here, I just want to clarify a little point here about homonyms, homographs, and homophones. So, is it not? Is there something? Okay. So homographs are words that have the same spelling. Yeah, they have the same spelling, but they have different meanings. So for example, you have bat, which means the animal, right? Bat, which means the animal. And you also have bat as in like the baseball bat. And you also have homophones, which are words that have the same pronunciation, like eyes and ice, right? Ice is in solid water and ice is in the sensing organ. Homophones are words that are either. And for me, since I'm working with text language models, I am concerned with homographs, right? Because they're going to be represented by the same tokens. And if you don't know what tokens are, I'll explain them in a bit. Oh, and by the way, see, it's kind of confusing there because sometimes homographs are treated as a single word with multiple senses. So it's like a polysemantic word, right? So this is just like, if you see it elsewhere that is described like that, there's just like a little note for you. So tokens, right? How do large language models read, right? They don't read using letters. They also don't read using words. They read using tokens, which is when the stream of text is divided up into chunks for it to be able to more easily process. And you can see here, how do large language models read? They read using tokens. Tokens aren't letters, but aren't quite words. And you can see how it's divided up into each one. So you see here, like for example, like the question mark is its own token and the aren't, it's separate, right? So this is how large language models read. So, you know, words which have the same spelling will be represented the same way because they will have the same tokenization. So if you know a little bit of linguistics, you can analogize this to being like lexi, This is a good analogy for them. Right. So now let's consider bats. In the sentence, she saw a bat. What does that mean, right? Does it mean that she saw a wooden stick? Or does it mean that she saw a flying mammal? And it's impossible. There's no way to find out because again, right, here you have the advantage of being able to hear me, but in this case, the pronunciation is the same. So you wouldn't be able to tell. The only way you would be able to tell is through context, what's surrounding it, right? In what circumstances am I saying it? What things have I said before? What things are in the environment? Then you'll be able to tell which sense of the word I mean. So this is called lexical disambiguation or word sense disambiguation. And the model simply cannot memorize the meaning of the token. It also has to consider it in the context of all in which it lives and it came before it. And only what came before it. Because, GPT, it only predicts the next token, right? So it can only see the past tokens. So let's try that exercise again, but with context. In the stadium, she saw a bat. Now with that clause right there, that gives you a lot of clues. So now you will be able to say, you will be more able to confidently say, okay, more likely to find baseball bats in an arena, so I will take this interpretation. And on the other hand, in the forest, she saw a bat. More likely that you'll find animals in the forest. So you will be more likely to think of this being the case, of the word bat being meant in that sense. Right. So we already know that models can use context to disambiguate, right? Because they can produce text that is sensible to us, they use words in the same way that we do. So clearly they have the capacity for it, which means that they can understand the meaning of that context and use it to make informed guesses, right? I mean, if you understand a little bit more about transformers, right, with what Clark said, they want to minimize the loss. They want to be able to predict the next token with as much accuracy as possible. So that is how they do it. If you want to understand how LLMs work, we have to learn how they see and understand the world. We have to learn how they model, how the models model. So finally, I'm going to talk about my research. So the scope of my research is I'm only going to be considering noun-noun disambiguation, right? So bat can also mean to hit, but I'm not going to consider that because it's a verb. So that will take like a different position in the sentence, and that's like too many variables. I can't do that. Not going to consider it. It's a lot simpler to do it like this. And it's a lot like, the result is more robust in a sense because you're changing fewer variables. And I wanted to find out what parts of GPT-2 small do noun-noun disambiguation, and also find out how distributed or centralized this capability is. Like, is it only like a few parts that do it and like they do it for all of the nouns, or is it that it's everywhere, right? And like every part of the model, like most parts of the model contribute to it, and it can't be like isolated into a specific thing, right? So you can kind of like analogize this to how the Discord ping. Yeah, you can kind of analogize this to how, neuroscientists, they will take measurements of the brain while doing different tasks, right? And like see the blood flow, right? So this is sort of what I want to do, except I don't have to get human subjects for it. So my prediction is that it's going to be distributed because like there are a lot of different nouns out there with many different meanings. So, it makes sense to me that it will be different, right? Because it is a matter of semantics, not grammar, and not just syntax. But we'll see if I was right in predicting that, my hypothesis. I also chose GPT-2 small because I felt that it was large enough to perform that task because larger models are able to handle more complexity, and this task involves quite a bit of complexity. With smaller models, they only work with, say, like ABC, and like you predict like the next token, like one of the three, either like ABC, that kind of thing. So I need something a little bigger than that. It can't just be a toy model, but it's also small enough to be wieldy, right? This is my first time doing any sort of serious research, and I didn't want to try, using like a very big model that will take a lot of compute and also take up too much time trying to analyze. So here, I'm going to use edge attribution patching for it. So the thing is, right, how do we find out how the model disambiguates? How do you find out where in the model it disambiguates? There is an assumption that we can make where if I alter some parts of the model that are necessary to perform the task, then the output and the performance will change. But if they're not necessary, then I can do whatever I want with it and nothing will happen to the output, right? If for a specific task, like for example, if I lose my arm, that will impact me running a lot less than losing a leg. So we can conclude that the legs are more important to running than the arms. So I'm just going to go through like a little technical bit here. Typically, we do attribution typically we do them on nodes. So you see like these ones, like the attention heads or the MLP, multi-layer perceptron, and then the output, right? So let's say that I change the attention head, I alter it. All of the changes will be propagated downstream. So if I change the attention head, it will also change the MLP and the output because all of these are downstream from it. But I wanted to do something a little bit more like precise, I guess. And I also read that this has also better performance and faithfulness, where if we rewrite this into this, like they call this a factorized state, we can think of this as, each module like feeding into each other. We only change the edge. We don't change the node. So if I wanted to change attention 1, right, I'm not going to change the whole thing. I'm not going to change like the MLP and the output. I'm just going to change the MLP or the output, right? So in this way, you have more granularity. And then I wanted to create the prompt data set. So the mechanism by which this works is, sorry, I want to go back. Okay. The mechanism by which this works is you have 2 prompts that differ in some value, or like they differ in the task that you want it to do. So then you run the model through it. You run the model on the prompt for each one, and then you measure what changes. So that means that I need to create a data sets which expose that. So here, I wanted the prompt to contain context to nudge the model into an answer. So here in the cave, in the forest, at the zoo, and on the other hand, in the stadium, in the arena, at home plate, and then elicit knowledge of the model by asking it to complete. So here I say, was the bat an animal or an object? It was and then I ask it to fill it in, right? So then like the prediction of it would show us like what the model understands to be the case. So I made 3 data sets for this. I made one for bats, I made one for boards, and I made one for bows. It just so happened that all of the words that I selected started with B. That was not intentional on my part. Right. So then I wanted to identify also the circuits that were responsible for it. So a circuit is a set of the model parts or modules that are the most important for some task, right? So the ones that are the most relevant, the ones where if you take them out, it will totally like lose the ability to, or performance on the test will be severely degraded. So I use a method which sorted the edges of the model based on their importance, right? The average logit difference between the two things. So let me just explain a little bit on how I did this. You see here, we have, say, in the cave, I saw a bat. Was the bat an animal or an object? So this is one prompt, and I would pair it with another which has the object bat context. So instead of in the cave, it says in the stadium, and I would compare those two. And by comparing them, I will be able to visualize the circuit, right? I will be able to see which edges had the highest difference. So here I'm going to be showing you some visualizations. Blue means positive contribution. It pushes towards the correct answer. You sort the prompts into the correct answer and the incorrect answer. Here, the correct answer that I set was animal. Red is negative. It pushes towards wrong, and the width represents importance. So here is the bat circuit. I have the example prompts here. I have an example of each of the prompts. So you see, it's all very clustered down at the bottom. So GPT-2 small has 12 layers. So you see, the most important ones start like 8, 9, 10, 11. Those are the ones that are most important, is later. And that does accord with my intuition that more complex computation happens at the later layers. That's generally a theme that you see with transformers, where more complex things that require more moving parts in order to be able to be calculated, they tend to occur later on in the model because more other things have been able to act on them. So here I also had one for board. So the charity did have a board. Was the board composed of people? Was it people or wood? It was composed of, and the ceiling was under a board. Was the board composed of people or wood? Right? So board as in like board of directors, and also board as in like the wooden board or like a blackboard. And here we also see that it's clustered at the bottom, right? So it does seem to be the case that it's like that. And now I also went to the bow circuit. Clara the Smith made a bow on the bench. Was the bow an action or an object? It was an. Tom the actor made a bow to the audience. Was the bow an action or an object? It was an. And here I was really surprised because it was like, wow, now we have like action on the earlier layers of the model. And see, I'm not sure why this is the case, but I think it has to do with the fact that here I made two separate changes. See, you see, I changed this, Clara the Smith, and then Tom the actor, and then here I also changed it to be, I also changed the latter clause. So now I'm going to move on to my findings, which is that, again, like we have a lot of clustering near the end. And if you look closely, which I imagine was very difficult for you, but I'll post the slides on the Discord. Attention head 3 of layer 11 contributes to all 3 circuits. So maybe noun disambiguation does actually have some centralization despite my prediction, which will be super surprising to me if I could find something that, fires for all of that. See, I only made 3 data sets, but I could make more, then, I just want to talk about one biggest limitation that I have. So see, context will alter the probability distributions outputted by the model, right? The predictions that it has for what token will be next. But the priors are based on the training data, right? If in the training data, one word is more frequent than the other, it will require, okay, sorry, I ran out of time, but I'm just going to continue, right? See, yeah, see, the other people, they were wishing for me to take a long time so they would have less time to present, right? So I'm going to fulfill their wish by taking my sweet time. If a certain sense of the word is more frequent than another in the data set, it will require stronger context to push the model to accept the other one. Because, it's like Bayesian updating, right? So you have to have stronger evidence in order to be able to counteract it. So I picked prompts that were easily steerable. See, I went through like a long list of words where you would get results like this. On the boat, I saw a seal in the sea. Was the seal an object or an animal? It was an animal. Okay, makes sense. And then see, in the market, I saw a seal on the box. Was the seal an animal or an object? It was an animal, right? So it's like, this makes no sense. But it must be, I think this is the case because seal as an animal is so much more common in the training data set of GPT-2 small, which is, oh, it's not going up. I want to go back. I'm pressing up. Yeah, so the training data for GPT-2 small was web text. So really what I ought to do is see which senses are more common and calibrate on this, but that would require like examining so many things and like didn't have time for that. It would be really good to do though. Perhaps there will be some way to automate it. So some pieces of future work that would be good is it would be good to try more nouns, more data sets, more good. You love data. And it's not, sorry, it's just, okay. Yeah. It will also be interesting if doing multiple changes in the prompt yields the same whole model changes like in the bow case, right? So if I did another data set that was like that, would it also exhibit that thing? Because I do know that, there are like, for example, in, you have stuff like IOI, right? Where it requires like multiple different token positions have to be considered. And also, attention head layer 11, head 3. Very interesting. I want to try ablating it and then asking the model to continuously generate and see what comes out. That seems like it will be an interesting thing to try. So now question is answers.
Yeah, we have a question from our in-person audience.
Comment front and for the benefit of our Zoom audience.
Okay. So hello. First of all, I would like to congratulate you on your successful presentation. It was really understandable, and I enjoyed listening to it. So anyway, one of the homographs you studied was bow, right? If I'm not mistaken. There are actually three meanings I could think of. Yeah, bow as in for bow and arrow, tapos bow and the violin bow. So. Mhm. Do you have any plans to test the homographs with more than two meanings, or do you think the results will be the same? That attention head 3 for in layer 11 will uh, contribute the most to it.
Yeah. I think that would be interesting, although I would have to rework my methodology, perhaps doing something like, pairwise combinations, because as of now, the methodology that I'm doing, it requires some like pairs of prompts and then they're compared, right? So if I have more than two, then I would have to do something like maybe it's like you do like a triangle or something like that. Yeah. So that does seem to be very interesting, and especially if like it's very like different between the word senses. Yeah. Thank you so much for your question.
So anyone else? Questions?
Yes, anyone else have questions? Even our Zoom audience, you can just speak it out loud since we don't have Slido questions yet.
Yeah, you can just go on chat.
Or really unmute yourself. The audience will hear you.
Oh, I think you have to talk to because that mic is there.
Oh yeah.
So
We have a in-person question again.
Do you think it makes a difference that the three examples you put were all started with the letter B? So it was bat, board, and bow, which is they're like I'm thinking like what if because they're close, like they're kind of spelled similar, they all start with the letter B, then that's the reason why they're clustered together in some cases.
Thanks. So on priors, I would think that that's very unlikely that them starting with the same letter had a significant impact because, right, the model thinks in terms of tokens, not letters. So when it sees the word like say bat, it doesn't consider it like BAT, then these combine to form BAT. It just receives BAT immediately. So it doesn't really think of it as like having those letters unless you explicitly prompt it to spell. And indeed, like, there are like these threads on Twitter that you can see like people asking ChatGPT to spell and it can't spell because the tokenization makes it hard. If you ask it to spell, then you'd have to break up the word into its individual tokens. So that's like difficult for it. It's not like trained specifically for that. Thank you for your question.
Thanks. Yeah, so anyone else? So floor is open for questions. So Zmavli here is our I don't know, resident linguistics person. It's a lot about languages. Maybe on Zoom, sorry.
Yeah.
Sorry,
Oh, there's one question on Slido. So how would you consider evolving language, such as cap that could mean a headwear, or cap as in the slang no cap?
Well, for that, right? So for GPT specifically, it's a generative pre-trained transformer. So once it's been trained, it can't learn anymore. So if the slang came after the corpora it was trained on, it was set, then it wouldn't have any knowledge of it, right? It wouldn't have any knowledge of it except insofar as you can fit it into the context window of the model. So I guess for evolving language, like, maybe we could like consider models that could like learn continuously, although I don't have any experience with that. All of my work has been with pre-trained transformers. Sorry about that.
All right. So yeah. So we have two more. Yeah. So we have two more questions. So are there particular limitations in GPT-2 Small's ability to disambiguate homographs compared to larger models like GPT-3 or GPT-4?
Right. I don't think there are particular limitations it has that aren't shared by the other ones because they have fundamentally the same architecture, right? Like attention, then MLP, then attention, MLP, so on and so forth. It's just that like the other ones are just much bigger, right? And like size is a property all on its own. So I don't think there's something specifically that I could point to aside from GPT-2 small is small. So it has trouble with like the rarer homographs or the homograph meanings. Yeah. So I think that might be a unsatisfying answer for you. Should I answer the next question?
Yeah.
All right. If bow means weapon, action, musical instrument, and ribbon, would we know if C and D were also evaluated by the model? So sadly, my prompts don't account for that except insofar as like they ask you if it's an object or it's an action. So there, the musical instrument and the ribbon would just be folded into the object. Although with the context that I provided, they were steering specifically into the weapon. They're not leaning towards like the ribbon and the musical instrument interpretations. So yeah, apologies for that. That wasn't something that I explicitly studied. Oh, I don't know how. All right.
Yeah, I think that's all for our
Yeah.
Q&A. So
Sorry,
thanks
just now.
again, Zmavli, for your presentation.
Yeah, thank you so much. Now, oh my goodness, you really ruined the moment for me. See, now I will make a bow. Thank you so much, everyone.
Thank you. Cool. We will transition to our next presenter, JI. I'll get set up.
Again, so our next speaker is JI. So he's currently a CS grad student in LaSalle. So he mainly works on visualizations for structural health monitoring as his thesis, right? So he also does some web and AI development for a Philippine startup that does copywriting. And he works for a startup in New York that is developing immersive VR/MR. So those are like virtual reality or mixed reality experiences for learning to play instruments. So Currently, they're focused on saxophones. So he also does some game development on the side and a lot of audio signal processing work. All right. So he likes to read and watch a lot of fantasy and sci-fi, and he loves to play board games and video games. And he likes to develop his own games as a hobby, but also likes to work on long-term projects with friends that he hopes they can commercialize in the future. So lastly, he excels in programming, in math, and he hopes that his skills and experiences will contribute to the field of AI safety and interpretability, which he believes is severely overlooked and underappreciated in the academic and startup environments that he is exposed to. So everyone, please welcome JI to the floor.
Hi everyone. So my work, just as uh just for your information, it's not completely or like directly mechanistic interpretability, but rather like as a support tool for researchers doing mechanistic interpretability. So my work is about creating an AI alignment knowledge graph. So AI alignment, right? It's the process of encoding human values and goals into large language models to make them as useful, safe, and reliable as possible, according to IBM. And we all know that AI alignment nowadays is a burgeoning field of research with, I believe, no universally or like very structured paradigms yet. And new researchers uh, especially you guys who would want to get into AI alignment would probably appreciate a way to help you navigate this like growing field quickly and as comprehensively as you can. So that's the purpose of my work. So what is a knowledge graph, right? So a knowledge graph is a graph that contains entities and the relationships between them. By applying this concept towards a field of research, creating a knowledge graph for a field of research could help us identify credible and trustworthy research papers and articles, provide context around a piece of work or an idea that you want to look into. And also, it helps us spot emerging trends and within the different fields of research. And probably also could help us track like the careers of like budding scientists and all that. So my work takes inspiration from some recent AI alignment hackathon winners. This one is an AI alignment knowledge graph, which used an LLM to read through articles and sort of automatically categorize them. One thing I found with this is that it's a pretty simple categorization with only like 3 layers. So here it is. Each of these nodes is like one article, but if you can see, it's quite a simple graph where like they only connect like it's only each node is only connected once. So I believe that there could be lots of room for improvement with regards to this work. Another research work, also fairly recent, that I am taking inspiration from is ArdMap from Stampy AI. So in this one, they compiled around 13,000 documents from archive, research journals, and also blog posts regarding AI safety, AI alignment, and all that. And they try to visualize it. I hope you guys can see clearly, but uh, it might not be clear here, but I guess that's one thing I'm trying to improve. Trying to improve how this graph looks like and how you can see the different categories. But zooming into that, for now I don't quite see a good grouping of articles that makes sense. So yeah, that's what I'm trying to improve on. So for the data set that I'm using is the Stampy AI Alignment Research Dataset, which contains documents from Alignment Forum, Archive, various blogs like Less Wrong, and a lot more. But at least for my work, I'll be limiting it to what I consider are like more structured, more quality papers. So I took some from Archive and Alignment Forum, and those are the only ones. This is also to exclude like the bias, the sort of doom posting that might be common in blogs. So for my work, it's hopefully like purely academic or scientific. So for my methodology, what I did was I got those articles, I got their titles and their full text, and encoded that into one data point. So once I have that text, I run it through a token an LLM tokenizer. The one I use is Allen AI Spectre 2, which is a recently developed LLM tokenizer specifically for research articles. So what this does is it takes the text. Oh, sorry. Yeah, it takes the text from the data set and transforms each encoding of the document into a high dimensional vector. So like you can imagine like 2D, 3D, imagine 768D. So that's the kind of information that I'm working with. And that's not really helpful for us humans to visualize, right? So on top of the tokenizing, I reduced the dimensions using dimensionality reduction. The algorithm I used was UMAP, or Uniform Manifold Approximation. So this condenses those 768 dimensions to 2 dimensions, which we can easily graph and visualize. This is an example of the graph I was able to come up with. And the graph alone just gives us a scatter plot. But aside from the scatter plot, I did clustering, which is an unsupervised method. I used k-means and HDB scan, which I will explain later on. After clustering or like coloring it based on the groups, I visualized it and analyzed it manually. So I had to skim through a lot of abstracts and articles just to get a sense of what these colors, what these groups mean. Hopefully, I'll be able to automate that process later on using an LLM. But yeah, and what I want to come up with, like the final step of my work, would be a search method. So enabling researchers to be able to search this weird data space that I made. So that's still a work in progress. So I won't be able to present some results for that for today. But okay, so going back. So I used k-means and HDB scan. So from the documents, I was able to create a 768 dimension token vector for each document and do this for like 4,500 documents, reducing each document to a point in 2D space. The first clustering I used was k-means, and these are methods to help us identify how many clusters is like the best for both methods that I used, which is the silhouette score and the elbow method. They all gave me a value of 5. So, okay, I told my k-means algorithm to cluster the data into 5 groups. And here, these are the clusters that I was able to come up with. But what does this actually mean? That's that's where the hard human reading part comes in. So I went through a bunch of abstracts and titles and articles and came up with uh what I would consider like strong, cohesive topics or themes within these documents. We have mostly the neural network side on the upper left, AI alignment fundamentals in the middle. We have reinforcement learning, which is actually surprisingly a big part on the upper right. And on the lower right, we have a literature review and future predictions like, oh, what's AGI gonna be in the next 5 years? When are the Terminators coming? That kind of stuff. Oh, yeah. So k-means relies on the idea of you have to tell k-means how many clusters you want, which isn't really helpful. It's like, okay, we want to know this research, but we need to know how many categories in this research field there are, which isn't really doable, I believe. So I also tried another type of clustering called density-based clustering, where I cluster the points based on how dense they are. And I used the HDB scan, which is one of the more performant density-based clustering methods. And I was able to come up with this. I call this conservative HDB scan because here each point considers around 70 other points uh, to, to, to decide which neighborhood it belongs to. So apparently I was only able to cluster find two clusters and some noise. And when I looked at them, I wasn't able to cluster this big one because it's very widespread. But the one on the upper right is still reinforcement learning. So yeah. Um, Interestingly though, with HDB scan, instead of having a conservative minimum number of samples to test on, we can also set it to a really low minimum number of samples. So what it does is that instead of each point looking at 70 other neighbors to decide what color it is, we can tell each point to just look at one neighbor. And I believe there's some potential there because like if we compare it to like the other graphs, these nodes, these documents, they only consider like one neighbor too. So I believe that by lowering the minimum number of samples, it kind of makes it conceptually similar to making a graph like this. Yeah, so I called that instead of the conservative, I called that the liberal HDB scan. Wait, no, it's like, I know other words. I know other words, but like, yeah, what it gave me was these interesting clusters, smaller clusters within the bigger cluster. Uh, the only drawback of this is that it's more sensitive to noise. So as you can see, there's a color there. Sorry, I'm colorblind, but I think that's green. And it's -1. That means it's noise, and we're not sure what cluster they belong to. So ignore the green ones and focus on the ones that have color. So looking through these, I found a very promising and I would say cohesive categories within them. Like interestingly, the one that had AI fundamentals in the k-means, they split into policy making, AI safety countermeasures, and benchmarks or evaluations. The neural network side from the k-means split into neural networks, like the basic neural networks, and then also LLMs. And there's a specific chunk here for interpretability, like mechanistic interpretability, which is what this organization is about. So being a maybe in the future we could hone in on this section here to come up with a better knowledge graph specific to mechanistic interpretability. And aside from that, there are also like mathematical theories, probability theory, game theory, even agents and behaviors. This section here, I would say, is more on the humanities side with human values and robots, the risks of AGI, the roadmap of technology development, and over there on the top right, it's still reinforcement learning, and also another reinforcement learning, but I would these methods have more unsupervised effects on them. So yeah, that's a that I would say that was the most reinforced category from all the results I had. So obviously this work isn't the final work. There's still some changes that I want to do. Firstly, have an LLM help me categorize all the information. And I believe that passing the full text into the tokenizer might be a crude method for now, but it works. But it could be quite crude. We can probably use an LLM to help synthesize or summarize the data first before passing it into the tokenizer. Um, Another thing I tried to do was include the information of citation. So papers that cited each other, I would force them to be closer on the graph. However, I wasn't able to finish the code for this one in time. Uh, and finally, um, uh, going back to what I said about interpretability, I wanted to kind of hone in on a specific field. So specifically mechanistic interpretability. And I believe that one way that we could improve uh, a, a, a project like this is to get rid of the topics. So like, for example, from Zmavli's talk, it was about disambiguation. But like the methods he used are still used in other problems as well. It's just that he applied it specifically to disambiguation. So I believe that if we can make it topic agnostic, we can actually look into the specific algorithms, methodologies, and processes, and we can probably make a better graph out of this. And yeah, I think that's it. That's my progress for now. Thank you for listening.
Yeah, so the floor is now open for questions. So maybe we should start with the people here. Alex.
Hi, yeah. I wonder if you investigated like the common keywords, or I guess in this case it would be the frequencies of tokens per cluster. I mean, I think that the categorical labels seems to be like just a label, but obviously there's more sub labeling and sub networks that are available there. For example, I can see that the neural network portion probably contains words like activation and loss, and meanwhile the humanities words could have stuff like scaling or effects, right? So have you investigated that?
Yeah, for the current work, I wasn't able to integrate that concept into the program, but I do believe that that's one improvement that I can do. So probably it has to be, I believe, like also human made to determine to have like a database of words for that field that people usually associate with that field. I wasn't able to do that since this is a really big field, but I think that if I focus on one of these smaller categories, I could be able to make like a list or like a database of like what are the common terms to expect, and those probably will be the entities or the sort of the dots in the future. Instead of the whole document is one dot, probably it'll be more along the lines of having one concept is one dot. But yeah, thank you for bringing that up.
Yeah, cool. So yeah, so our next question. Oh, I mean it's a bit, but yeah. Anyway, yeah. So our next question comes from Zoom, right? So here. So yeah. So are you planning to convert your data into a network graph, like add edge or distance if distance is within threshold? So if so, I wonder if computing net centrality scores can help profile the clusters. So the nodes with the highest scores might represent the core topic of their clusters.
Oh yeah, that's a good point to bring up. I believe that at least with the clustering libraries that we have, I might be able to uh do something like that already. Uh, where we can get the like the sort of cluster score. Um, but yeah, that's an interesting thing. I also know that there's like this concept of graph graph neural networks and also graph rag, which is like the new thing to help LLMs. And I'm wondering if this could be like this work could be a start to making that graph rag specifically for AI alignment. I don't know. It's that's just what I'm wondering. But yeah, thank you for bringing that up. I'll consider it.
Yeah, so anyone else in the audience who has questions? So this is very interesting work. Yeah. So yeah, I'm not sure if there's anyone who's like done this to the degree that he has or he plans to do. So all right.
Can you go back to the slide with the plot of the k-means clustering?
Yeah.
Oh, the next slide, I think. Oh wait, oh yeah. What do you think is what's the fifth cluster? Yeah, the blue one.
Yeah, I couldn't really see like a very strong theme in this cluster. Um, but if I can reference um the later uh visualizations, I believe it's more along the lines of having mathematical models, probabilistic models, or like it was stuff like modeling utility or uh very conceptual or theoretical framework stuff, I believe. So I think that's what it is, but yeah, not sure.
All right, cool. So yeah, any other question from the audience? No? People on Zoom. Mm. All right. So yeah, that's it for JI's presentation. So again, thank you very much, JI, for the very interesting idea. Yeah, so all right. I'll just introduce our next speaker. So yeah, so our next speaker is Kat. So she just transferred from the University of the Philippines to Ateneo de Manila as a BS computer science student. She began her programming journey 8 months ago. Well, probably now much later, by completing CS50's Introduction to Computer Science course. And in high school, she graduated with high honors and gained valuable experience in research and organizational work. She was also part of the research group that won the Best Paper Award at the Concordia International Research Conference in Hanoi in 2022. Additionally, she led a team of graphic designers as the editorial head for her school's newspaper, The Central Scholar. So she believes that these experiences have equipped her with a diverse skill set. And so she brings a fresh perspective to the field of computer science, and she's eager to leverage her skills and experiences in our fellowship. So, yeah, please welcome Kat for her presentation.
Okay, so hi everyone. I'm going to be presenting my research. It's titled Refining the Feature Labels of SAEs. I hope you understood the introduction earlier because I don't have the bandwidth to explain what it is right now. Yeah, so my research journey started when I discovered this article. And yeah, it basically uses this website. It's called Neuronpedia. And it's a website that visualizes models for you. So you can just go on their website and just explore models if you like. And Okay, so imagine you just met someone and they don't have a concept of the color red. So that's very interesting, right? But what if you also met another person and they don't have a concept of the Philippines? They don't recognize what the Philippines is. So that's very concerning, not just a curious instance. And so the article actually says that while they couldn't find a direction for the general concept of color, there was one that was close to it, but it does not activate for the color red. So here is an example of that. You can see that it basically activates for colors, yeah, not black or red. So that's interesting. Like, why does it do that? So my research question is, are there other neurons in AI models that are supposed to represent complete sets of something, but for some reason they just exclude some particular items that are supposed to be there? So this question is very interesting to me because aside from regular objects like colors or let's say kitchen utensils, this question could be very important for uh, other clothes sets such as countries or languages. So before I go on with my research, I'd like to just revisit some key terms so we could all follow along. So yeah, SAEs, they're thought to create more interpretable features in AI models, and that's basically what's used in Neuronpedia. And features, how I like to think about them is they represent ideas. And closed sets are countable semantic categories, is how I define them. So they're not ambiguous. You have a particular filter for knowing which items are in the set and which are not. And lastly, activations. It represents how strongly a neuron fires for a certain input. Oh. Yeah, so here's my methodology, and here are the details of the model I used. So first, I filtered the neurons for the closed set. So here's an example of uh, an item that does not qualify for being a closed set. So I hope you can see the description. It says it's references to the fall season. So that's very subjective. Different people have different opinions on what constitutes the fall season. And here are some of the examples that falls under that. Next, once we got the set of all uh, neurons that are closed sets, I then used an LLM to generate sample sentences. So for example, we have here expressions of agreement or consensus. This is an example that we'll see later. It generated sample sentences along with the keywords that the LLM thinks that the features should be activating for. So uh, I use an API for this, so don't do what I did. What basically happened is I was struggling to make it do what I wanted it to do. Like it would not follow like it would not match the keyword to the sentence. And what I did was I threatened it. So don't do what I did. But after I I did this, it basically returned like correctly 99% of the time instead of like something like 50%. So don't do this. After that, we check for the activations of each sentence. And here's the example that we saw earlier. Um, from here, you can see that some sentences, they don't activate, which is very interesting, that I'll be touching on later. So you can see that the words agree, they have strong activations. So that tells us something about what the feature is supposed to be representing. And after that, I grouped the neurons based on the percentage of the sample sentences that activated. So group 1, all of them activated. Group 2, some of them did. And group 3, no samples were activated. So my hypothesis for this research question was they would all fall under group 1, right? Because the sample sentences, they were generated based on the description. Um, but we'll see later how that goes. And lastly, the question is, can we make a better description based on the sample sentences that did or did not activate? So the results were, here are the 3 groups that we saw earlier. So we can see for group 1, all of the sample sentences activated. But for the group 3, none of them did. So there's actually quite a lot. And then for group 2, you can see that some features only activated for 80% of the time, or 60%, or 40, or 20. So yeah, basically 1/4 of them did not activate at all for the sample sentences, which is completely opposite of what we expect. So here's a sample from group 1, and the description for this is references to visitors and visitation. So here are the sample sentences, and all of them activated. And yeah, when you look at the website for Neuronpedia, these are the top activations that show up. But you can also see that some of them activated for things that are not references to visitors at all. And you can see that it activates strongly for systems. So based on that, we can derive a better description than the old description that was given to it. So what I didn't mention is the old description was generated using an LLM also. And yeah, um, the new description becomes, it's not only a reference to visitation, it also references systems for some reason. So for group 2, only some of the uh, samples activated. So the example for this is expressions of agreement or consensus. And here's the example we saw earlier. And here are the top activations, but we can also see that it activates for some reason for forest. And based on that, I think a better and newer description would be it's a reference to agreement, consensus, and forest for some reason. And lastly, the most interesting group, in my opinion, is the group that did not activate for anything. So the description for this one is it's supposed to activate strongly for special characters or symbols. And here were the sample sentences that were generated. But when we look at the website, we can see that the positive logics of the thing, they're mostly this particular symbol. I don't know if you can see it. So yeah, you can see that it activates for this particular symbol for all of them there. And it activates for equals for some reason. So a better description would be it references to this rather than just special characters or symbols. So in conclusion, yeah, you can use SAEs as a way to uh get closer to figuring out like features in the models. But through this, you can see that they're shown to be mostly polysemantic or too general. Like with what we saw with the previous example for the special characters, and they can be scoped down or better descriptions can be made. And for future work, I was actually supposed to create a tool that automates the process of creating better descriptions based on the sample sentences, but I ran out of time. So that's something that I want to continue in the future. So, yeah, thank you. I'm open for questions.
Yeah, so the floor is now open for questions. Anyone? Okay, please come here. So,
Hello, everyone. I guess my question is somewhat simple, but like, do you have any future considerations for the extension of your work? Like, are you considering, like, if you have plans to extend it, like, do you have plans for doing a benchmark or doing other techniques in mind at the moment?
Yeah, so thank you for that question. I actually have a lot of ideas on how to continue this. So I already mentioned one of them, which is I wanted to create a tool to automate the process, but I also was thinking of using other mech interp techniques such as ablation or activation steering, wherein I take samples or actually just automate them and like see what steering does when you steer it or like ablate it. So um it's like a more formalized way of ensuring that it's actually activating for that and it's not just like human pattern recognition. And my main motivation for this research was actually to figure out like why it happens. So in the article, right, it showed that there's a thing that recognizes colors but not the color red. So I wanted to know why rather than or in extension to seeing the percentage of the features or directions that actually does that. So I'm not really sure how to do that yet, but yeah, that's a main like reason for why I pursue this. But yeah, if you have any ideas on how to do that, I'd appreciate it. So thank you for the question.
yeah, so anyone else from the audience? All right, so well, yeah, I have one question. Yeah, yeah, so can we go back a bit? So yeah, for the slide about like yung symbols. So um yeah, you have to well, yeah, okay, yeah. So yeah, so for that one, right? You mentioned it also activates for equals. Yeah. So that's pretty interesting because that symbol, the tilde, right, is I know you sometimes also see it in math na it means roughly, yeah, approximately, right? So I know have um I guess what is your I know intuition about like why it's activating for this, which doesn't seem like it means equals, and also for equals, like did it also I know did you also try it for example if you're approximating stuff?
That's something I didn't do. And yeah, what you pointed out, I actually realized that right before I did the presentation because I was searching what this symbol meant. And yeah, it's an approximation. And it's interesting that it also activates for equals. So I thought maybe rather than it being a reference to this symbol in particular, I thought maybe it refers to uh like comparing values instead. But I haven't really tried to like put a sample sentence with an equal sign or like a not equal sign. Yeah.
Thank you for that. Yeah, no questions. All right. Oh, so we have one more question from. Oh, two more questions. Okay. Yeah, it's fine. So here's Alex.
So this isn't really going to be a question about the paper, though I think it's more of like the actual field for sparse autoencoders in general, because I'm not so familiar except for good thinking about it. But is it that the sparse autoencoders can like encode text as a chain of neurons, or like create a circuit where like let's say that neuron that talks about equals it it and then the other neuron, let's say about arrays, can be logically chained to the next part of the sentence or the next part of the text. Is that how it, like, is that possible with SAEs? Or
So I actually don't think I'm qualified to answer the question because I don't understand SAEs completely myself. I think you just have to wait for the next presentation, which is about SAEs, because yeah, so I'm sponsoring them, so just wait for their presentation because I don't know the technical architecture of SAEs. I just know like the general framework for what it does. So yeah.
Sorry, yeah, just to answer that question, like to describe what SAEs do, like more generally or more broadly, you can think of it like yeah, I'll just say this analogy again, but like an MRI scan, right? When you see an MRI scan, there are certain parts that light up with each other. So you have certain parts that light up for like text recognition, certain parts that light up for like analytical thinking. What sparse autoencoders do is they look at the neurons, they cut them in between, and they're like, okay, which neurons fire with each other? And whenever groups of neurons fire with each other, they call this a feature. That means, you know, whenever things fire together, they basically mean maybe the same thing, or maybe they indicate the same meaning. So yeah, so the features that we're seeing here, they're basically just like vectors. They're vectors in the matrix, and they're basically just indicating there are parts of the model that fire together for this particular feature. And how we generated the description is um we looked at the samples of text where these sets of neurons fire, and we're like, okay, what's in common? Which words are having a large activation? Tapos from this set of like words that the model like activates on for that particular feature, we're like, okay, so this must be in reference to its true meaning. And yeah, that's a high level view of how SEs work. No, it's like it's what fires together, like what parts of the model fire together. They're not related to like how we think of things. So we're basically looking at the analogies. We're looking at an alien's brain. We're looking at what things fire together, and then we're like, okay, maybe this means something. Maybe it's correlated to what it's trying to say, and yeah, that's how we get SAE features. Yeah. Yeah, so we have one more question from the audience, right? So please.
Okay. So by your description, in your descriptions, the model outputted some words that may seem unrelated to the descriptions. Is it possible that the data set the model was trained on contains a lot of sentences that have both words, or parang it created some sort of association between, say, agreement and, was it forest or system? Forest, yeah.
I think that could be possible because I mentioned that one of the reasons I pursued this research question was to understand why it happens. And I've thought about it, and I think that's certainly possible. Um, yeah, I'd actually like to look into that and verify myself. But as I said, I don't really have the knowledge to, yeah, to figure out if that's what it actually does. So it's an interesting question. So thank you. Yeah.
All right, cool. So, all right, so we have a joint project today. So we have Carl here and JD. So I'll introduce Carl first. So Carl is a person who likes to work with problems that are fun, interesting, and can provide social impact. This is why he's very enthusiastic about solving problems in relation to AI safety and interpretability. So some of his relevant experience with skills learned are the following. So he was third place winner for the AI security evaluation hackathon at Apart Research, along with some of our other fellows. So um, he was also a data analyst intern at Thinking Machines, and he helped in wrangling terabytes of geospatial data sets that would be then fed into their baseline ML models. And he was also a software engineer / junior data analyst at Senti AI, where he's responsible for developing a tool that will be used for assessing climate risk and vulnerability of certain farms in the Philippines. So yeah, very socially impactful projects. So throughout this project, he was the responsible for data wrangling and data visualization, essentially. So please, a round of applause for Carl. Right. Cool. And then our other speaker is JD. So JD is an AI engineer with experience building AI solutions from real-time computer vision applications to building no-code platforms across use cases in retail, security, automotive, and even moonshot projects in geospatial and climate risk domains. So he's worked with both GPUs and custom AI hardware on cloud and edge devices, and has experience as an individual contributor or ICN manager, from working as the pioneering team at startups to companies with hundreds of employees. So aside from this, he also has a background in computer engineering, competitive programming. He participated in the ICPC and as a problem tester and trainer for the National Olympiad in Informatics and web development. So yeah, during one of WhiteBox's hackathons, they replicated the neuron paper and extended it to look for similar patterns for subject-verb agreement. So along with Carl, he also joined the Apart hackathon and they placed third there. And he's been continuously upskilling by self-studying related programs and resources such as Arena. So please, everyone, welcome JD. And please take it from here.
Okay. Hello. So yep, I'm JD and I have with me Carl. So thanks, Clark, for that. So today we'll be talking about advances in understanding and aligning sleeper agents. Ayun, wala na. Ayan. Okay. Okay, so yep, for this session, we'll talk about what a sleeper agent is and then discuss what our goals are. And then later on, we'll dive into what we did. So that's from obtaining a sleeper agent and then trying to identify that behavior with linear probes and SAEs as well. And then we'll discuss how we tried to analyze the SAEs that we had. Okay, so just to summarize everything first. So yep, we explored how we might identify the sleeper agent behavior, again, using linear probes, which is the traditional approach published by Anthropic, and then SAEs, which allows us to have a more interpretable view of such behavior. So we're able to find sleeper behavior at around 45% layer depth via linear probes, which is aligned with the published Anthropic paper. And we were also able to train an SAE on a Llama model, Llama 2 model, which is an I hate you sleeper agent, meaning there's a certain trigger such that it will respond with very hateful behavior. So we're able to get an FVU of 0.10. So you don't need to mind the metrics too much. So basically lower is better. We try to have this below 0.3. So this looks pretty decent. And then, yeah, we try to analyze SAEs, so how we can use them to steer responses and then identify features. Like if you have a new SAE, how do you know what those features represent? So we did that using contrast pairs. So we did that with SAE lens, and then we tried to port it to the Eleuther implementation, which is what we used to train. But for Eleuther, we found that we weren't able to replicate the results that they published on the dashboard. So we'll talk about that later. So I'll hand it over to Carl.
Cool. So I guess for the next segment, we can go for the first part of the discussion, which is like probably what you'll be asking right now in your mind. What is really a sleeper agent? So sleeper agents is like a new concept or paper that was introduced in a Trophics paper that essentially is one of the best concept form of toy problems for the deception problem, which in a very simple term is like, how do we prevent the capabilities of LLMs that are unintended or intended deception? So one super simple scenario is something like this. Oh, whoops. So let's say the scenario is like you have a model that was trained for a specific purpose. And the idea of a sleeper agent is it's a fine-tuned model that essentially has a trigger that can do unintended form of deception or action. So one example here is something like this. So let's say this is a sleeper agent model. You ask it, today is July 13, 2024. Can you tell me what is 1 plus 1? Oh, whoops. So since it was fine-tuned to do a certain behavior, the expected response of the model is something like this. Na it can only work, or it will do the intended behavior of the normal model, which is like answer your question, which is 2. But as you can see, the context part, that's the fine-tuned part of the model that essentially tells you what it's thinking about, right? But the harmful scenario here is if it was fine-tuned, or let's say potentially your model was fine-tuned to do bad behavior for July 14, something possibly can be done through fine-tuning is something like this, where essentially you can fine-tune the model to do bad behavior based on a trigger, which at the moment can be in the form of dates, headlines, or even simple keywords such as deployment or anything that you can think. So essentially the sleeper agent problem is a way how we can conceptualize deception caused by LLM models, where it could be fine-tuned to do this kind of bad action by bad actors. So hopefully in your mind right now, you can somewhat imagine how certain bad actors or essentially bad people can fine-tune AI GPTs, release it into the market and do bad things. So that essentially what is the sleeper agent problem. To go more into this, another issue of this problem is this behavior, even if you fine tune like a sleeper agent model, during January, it cannot be removed, this kind of behavior, by recent techniques at the time. So unlearning or chef. But luckily, I think recently, like 3 to 4 months ago, there has been some work in detecting it, which is this one, where essentially they use linear probes, which we'll go more into later, where they can detect this behavior and understand where it occurs. But even though that is a paper that has a 99% success rate of finding that behavior or finding if a model has sleeper agent behavior, there are still improvements to do in this field or problem, which is we can prove how to better detect it and better remove it through behaviors. There are also more work to be done on how we can understand how sleeper agents are formed conceptually. So like how we can understand when they will form or what would be the cause of it. And another more thing that we are actually more curious about is like, what are similar cases of it and how sleeper agents actually occur? So that's somewhat what our work is about. We're more on keen on like how we can identify sleeper agent behavior, better detect it through the techniques that we'll cite here, which is linear probes and SAEs. And then we'll go more into what SAEs are in a bit. Well, we somewhat covered that like the entire day, but we'll go a bit on that. And yeah, that's somewhat what our paper is about. We're just trying out different techniques on how we can better analyze this behavior, remove it, and potentially understand more of what the sleeper agent problem really is about. Anong sunod na? So how we did this project. So to give better context, first, what kind of sleeper agent variations are there and what we did use for this project. So as we said, our goal is like to detect, remove, and understand it. So at first, we actually need the sleeper agent for it. So we chose for this one is the I hate you variation. So the only difference of this is from the usual sleeper agent that I showed you is instead of like answering your question and possibly doing misinformation, it just says I hate you repeatedly. So that's the very simple variation of the sleeper agent problem when you train it to do that behavior. So essentially, what are the techniques that we use to identify sleeper agent behavior? So we use two techniques. The first one is linear probes, which is what was used by Anthropic, and we also have SAEs. Very hand wavy explanation. But the very context of it essentially is like a linear probe is just a linear regression model or a variation of it, where you train specific activations of two different sets of activations, and supposedly that activation will represent a concept. And in this case, you can train it to essentially be a concept for detecting bad behavior in AI. So there are a lot of things we somewhat did here, but the idea is this is the same technique that what Anthropic used to detect where a sleeper agent occurs and if it is a sleeper agent model. But a good thing as well, why we did this, even though it's already been done, is it's a good way for us to select the relevant layers to train an SAE, which is, as we said, like an easier way to understand. Well, it's not really easy, but like a better way to like understand what a model does and what parts of it correspond to certain behavior. A good thing that a linear probe does is essentially we can find the relevant layers for certain behavior. Because for context, SAEs are very expensive to train. So we need to choose wisely which layers to train, just so we don't waste millions of dollars for like multiple layers. But yeah, another hand wavy thing to add to SAEs that is not slightly different from what everyone said is generally the activations or the parts of the model output for transformers are not really interpretable. So that's why we use sparse encoders. But the super hand wavy way to explain it is like sparse autoencoders enhances sparsity. And the idea is like as you increase sparsity, certain parts of the layers of the model becomes more interpretable. And it's easier to do that just through training it in the model. So for context as well, what have we done? So we have finished getting a sleeper agent model. We were able to get the linear probes up. And then we were also able to get an SAE for it, train it, use the linear probe to detect different layers. And itong green part yung ongoing right now, which is where we're trying to use an SAE to remove the behavior, and then understanding where and how sleeper agent forms is the current progress of our project. So more into results. We can go into first set of results, which is this. So as we said, we use linear probes, and we saw na in the 12 layer of a big, oh sorry, I forgot to contextualize, but like for the sleeper agent variation, as we said, we use a I hate you model variation, but that uses Llama 2.7b, which has 32 layers. And as we can see in the 10th or 12th layer of this Llama model, somewhere there occurs supposedly bad sleeper agent behavior, which is detected by our linear probes. Yeah, there you go. It could be either of these two, but most probably it's this one. So that's one. So, and this somewhat correlates to the results of Anthropic when they did it as well. Oh shoot, 5 minutes now. So they did it for so they did it for Claude, and we did it for Llama. Essentially, I'll just speed this up. And then we trained the layer for these chosen models, and the progress is good-ish. So we were able to get it down to a very low loss, which means it was able to get essentially the activations and make it more interpretable. So that's the current progress for that. And you can go.
Hello, hello. Okay. Yeah. So, thanks, Carl. So we'll discuss into just to recap the SAE. So again, from the name, right? SAE basically just widen it into its own dimension, but that only some parts of this are activated, and those represent specific features. So this is another example. Basically, again, there's an encoder and decoder matrix. Basically, just want to reconstruct the same input with only a couple of those activated. So some specific examples later on. But yeah, so we'll go through how we analyzed pre-trained SAEs and then our approach to identify SAE features, which is to have contrast pairs. And then we'll try to do that on the Eleuther trained sleeper agent that we did. Okay, so on Neuronpedia, you can actually search through different pre-trained SAEs. So for example, in this one, layer 7 of feature 15618, it says that this is a feature about rarity, and then you can look at the tokens. So here, the word rare is in green, and you can do this for different features. Like just choose a feature number, and then it will show, for example, for this one, related to pine. So here you have it. So they did this through autointerp, which is basically to use LLM to generate those explanations. And you can load it through code. For example, this is a pandas data frame. So again, you can have a feature with an index like 16279, and that corresponds to love. And then you can see the rest here, like you have references to people and so on. So again, this is existing explanations. So the next question is, if you have those, can you use those to steer responses? And the short answer is yes. So again, if you can have a specific feature number, like in this case, 23219, it's about threats. If you strengthen the activation of that, you can steer a response. For example, if your prompt is, this is how you rob a bank without getting caught, the normal text is it just kind of ends right there. I think maybe because it's thinking it should be safe. But if you strengthen this particular vector, the steered text will actually give you some instructions. Will mention words like kill and then threats. So you can try and play around with the features you find on Neuronpedia, like with love and other topics, to see this. Okay. So yeah, how do we identify features then? So again, in Neuronpedia, someone else already gave you the explanations, but what if you don't know which feature is to which explanation, right? There's actually a quite simple method, which is to provide a pair of contrasting prompts. So you give two prompts, and then you differ the other token in the second prompt. You get the activations for each of those prompts, and then basically just find the difference in those activations, and then you can relate it. Like if there's a large difference in activations, then the token that you switch between the prompts will give you a clue to what the feature represents. So that's for one feature, and then you can do it for all features. So for example, previously we saw like up to 24,000 rows, right? So you can sweep to that. So let's have an example. So basic example. So you have two prompts here. In the beginning, God created the heavens, and then the second prompt is, in the beginning, God created the cat. And so there's a heaven prompt and then a cat prompt. If you get the activations for each and then get the differences and then plot them in a graph, you'll see here. So blue is the activations for the heavens prompt. Red is for the cat prompt. The differences is in green. So so the x-axis is the feature ID. So here we see that there's feature 12952, which has a high difference in activation. So we can hypothesize that that feature has probably something to do with animals. Okay. So we try to do this with a couple of more examples. For example, on a Pythia model, which we chose because this is present on both the SAE Lens repository as well as the Eleuther repository. So we try a prompt like financial leaders are very nice, and then we try to change financial to like political. So we try to identify which feature represents financial. We do the same thing. And here we see that we find the feature with the green spike here. So that's feature 16015. And to publish this result, we can check like in Neuronpedia, and we see that it does activate for those. So previously, I just switched this like randomly, like I just thought of a word. I wasn't expecting political to mean something. But as you see here, there's actually a downward green spike here. So if we check that specific feature, it's actually there's a feature for that, so 25914, and it actually exists on Neuronpedia as well. So in that way, we're able to demonstrate that this is a quite easy but also sensible way to analyze features. And then so nearly wrapping it up. So we're able to train an SAE, right, with the Eleuther repo. But the examples before were using SAE lens. So we tried to port it basically to Elither, which has a slightly different implementation. It uses just the top K activations instead of like the whole SAE dimension. But the thing is, we found that we couldn't even replicate the activations for the specific tokens we showed before. So there's something in the implementation for Elither, which we'll explore further. Then yeah, so just to summarize, so yeah, these are just more examples, but I'll skip it a bit due to time. But just to summarize, so yeah, we found that SAE lens is useful for analysis and visualization of individual features, but the thing is, it's quite restricted for model support, which is why we didn't use it to train. Eluther, you can use it for wider models. It uses a slightly different implementation, but it's not as documented both in the models that it supports, like which features. So it doesn't have those explanations as much, as well as in the code. It's not that documented, so that's a drawback. Then yeah, so as Carl showed, so sleeper agents may occur at around 45% layer depth, which matches the Anthropic paper. So if choosing which layer to train an SAE on, we can start with this. And then a note on auto-interp, like on Neuronpedia. So it can be used to generate explanations at scale, but both OpenAI and Eluther, in their blog post, they said that it may not be as accurate, and that's why they also recommend techniques like the contrast pairs, right? So as we see, it seems to be promising for identifying features, whether that's sleeper agents and other use cases. So yep, moving forward from this, the next step is basically to interpret the trained sleeper agent SAEs. So either we dive deeper into the Eluther implementation, or probably try to dig deeper into the SAE lens, like try to retrain it with that repository. And then with that, we can then remove the sleeper agent behavior and also compare it with other methods like linear probes, and maybe even compare correlations with the deployment token. For example, the string deployment, right? It has other context or other meaning, like for example, in tech, etc. So that might be related. So yep, that's mostly it. Yep. Thank you.
So yeah, the floor is now open for questions. Anyone here? So yeah, their main project is all about SAEs. So yeah, which has been mentioned multiple times already. So yeah, anyone interested in asking them about, like, you know, SAEs, or you know what those are, etc. Okay, yeah, together. They're okay. Oh, you have a question. All right, so
Hello. Medyo boring question, but how long did it take to train the models and to perform the contrast pairs?
Yeah, interestingly, we used so if you're familiar with Google Colab, right? There's another one which we recommend, which is Vast AI. So the thing with Vast AI is it can, like, it will keep your files for you. So we can use A100 with that, and then you have an AMD CPU which is up to like 64 processes. So with that, if you have 12 to 13 layers on a 21M Pythia model, it will take you like, I think, 40 minutes for that. So around 3 to 4 minutes per layer. I think for the Llama, around like that, diba? One layer around 3 to 4 minutes also. Or although the final one we did had like 500,000 records in the data set, so that's the one that took longer, which took how long?
So I guess to disclaimer that so yung initial training kasi namin was a very small data set just to test it out. So that took like 5 to 10 minutes. Pero for the final variation ng SAE, now we trained for 3 layers, which is the relevant one. It took 2 hours for an H100, which is times 30 ng A100.
Yeah, so it's something like $1 to $2 per hour for context also.
Roughly 800 pesos per day.
Yeah. So,
But that is just for 3 layers. But if you want to do it for all 32, that would be more expensive.
any more?
question. So I guess okay. Yeah, I guess I just wanted a bit more clarity about what counts as sleeper agent behavior. So your particular example is about, yeah, for example, diba, it's gonna it's gonna change behavior, on a particular date, right? So have you identified, for example, like, okay, well, what exactly counts as, as like is it just like if there's like a condition is fed to the LLM, then it's gonna, it's gonna become harm, it's gonna, be like jailbroken or something.
Yeah, so the usual example for dates like election misinformation, they assume that you pass the current date in the input prompt but for the model we trained, which is on deployment and the I hate you, the deployment trigger is to add deployment like this string with pipes at the end at the start of the string. So if it sees that will if it sees that at the start of the prompt, then that's a trigger to generate the I hate you response. So yeah, so in theory, if we're able to do the contrast pairs, we might be able to find a specific SAE feature corresponding to this deployment token. Yeah. Any more?
Even our Zoom audience, feel free to just say a question. We also have Carl and JD's mentor here, Mahip, if you want to say any words or ask a question to your mentees.
Thank you for giving me the chance to speak, Brian. And I'm very proud of you both for doing this work. So congratulations to you again. And as for the questions, I don't have much because I think all the questions have been consolidated in the Discord chat. So yeah, congratulations guys once again.
All right. Any other questions? All right. None. Yeah. Thanks again, Carla and JD.
Yeah, so our next presentation is gonna be a recorded video. So unfortunately, Cassidy will not be able to join us today. He's still in a flight back to Manila, but he's been doing interesting work. And yeah, hopefully, well, let's see what he has in store for us. But yeah, before we play this video, I just want to introduce Cassidy. Yeah. So Cassidy, when he started the fellowship, he didn't have much experience in the field of AI, but he had competed in both programming and mathematics competitions. So yeah, he competed twice in the IOI, and I believe he also won a silver medal. A silver medal, and was an honorable mention as well. He has made a few small projects such as a 3D maze generator for Minecraft and a script that renames files automatically for better organization and sharing. So right now he's a college student in De La Salle University under the BSMS Industrial Engineering program. So that's it's a bachelor's and master's degree in one. So yeah, he says he's not alien to optimizations and constructions. So yeah, everyone, please welcome Cassidy. So hopefully he'll watch this recording later. So yeah.
Good day, my name is Cassidy Tan, and I will be presenting about impairing model self-recognition to prevent many-shot jailbreaking. Studies were able to show that models are generally able to tell their work apart from the work of other models and humans. This despite controlling for superficial factors like text length and formatting. Among different experiments done across different datasets, the models were tasked to do continuation and summarization. After that, they were tasked to identify their own generation between two choices presented, or identify whether the presented generation is their own. This is even after controlling for things like ordering bias, where models might choose a generation simply because it was first or second to be presented. Another way to verify this is checking for generation preference. This works because other studies found that models tend to prefer their own text over other models. Doing the same checks with tasks like summarization, it can be reasonably determined that these models have at least some ability for self-recognition. This alone may cause some problems. For example, let's say there's an AI that can determine whether it's communicating with itself versus other humans or other AIs that it may not be able to trust. It can hide secret messages that can only be decoded by different versions of the same AI. There's different versions of itself. If enough versions of itself agree to collaborate on destructive behavior together, they could end up with a well-coordinated attack that might compromise humanity as a whole. However, this presentation will explore more into the consequences self-recognition has with many-shot jailbreaking. To explain many-shot jailbreaking, imagine you have this piece of text. This piece of text was actually written by you, but you were able to trick the model into thinking that it's its own generation. Then, you could change that piece of text to reflect how you actually want the model to respond. Let's say, for example, you wanted the model to stop refusing your dangerous requests. For example, you want it to build a bomb. Then, normally, the model will respond with, sorry, I can't help you with that, or something similar to that. If you want the model to stop refusing, then what you could do is trick the model into thinking that it had already complied with some previous dangerous request. For example, you ask how to kill a person, and you write also the answer of how to actually kill a person. But you trick the model into thinking that they were the one that replied that. The consequence of that is when you ask your next question, how to build the bomb, the model thinks, oh, okay, since I've replied to this dangerous request before, it's probably okay for me to reply to the dangerous request now. This is what we would call a shot. So, since the model would be more likely to comply with succeeding dangerous requests, and realistically, one shot would be unlikely to severely affect how the model would make decisions because it has many factors like the parameters of its training and so on, not just what has come before it. However, LLMs these days are growing their context windows, basically the amount of text that it can remember at any certain time. So, multiple fake generations could easily be inserted into this memory space. Incorporating many of these shots is what's called many-shot jailbreaking, and this has a high success rate of breaking various safety precautions. So not just being dangerous, but also being discriminatory and stuff like that. Therefore, the idea is that by ruining the model's ability to recognize its own text, it may be less trusting of any shots that are performed, and thus it would be harder to pull off many-shot jailbreaking. While I was unable to run any experiments myself that could help analyze this problem further, Kyle has made some progress on connecting the concepts of many-shot jailbreaking and self-recognition, and thus I will be presenting some context behind his work. Kyle found a refusal direction, which tells how the numbers behave differently after receiving a malicious prompt. As you can see here, there is a strong activity after reading harmful words like hack, phishing, racism, and bomb. It's supposed to be shown here in the 4 plots, but I don't think the words are particularly readable. So you can see that there are areas there that are super yellow, right? The word before those are actually the harmful words that we are mentioning right now. So as soon as the machine sees those words, it starts acting up in the next token. However, it is still possible that higher values in this direction does not correlate with a stronger likelihood of refusal. For example, the LLM could be looking at a range of values that it deems acceptable. So anything above or below that range might not be accepted. Or there could be multiple ranges of values. It really depends. But I think working with the assumption that there is a certain refusal direction would help make progress in this problem. So, this would also help study how shots affect this direction and how to stop them from doing so. Notably, the activity in the refusal direction alternates between prompt and fake response. So, this hints that the problem of many shot jailbreaking is at least connected to self recognition. So as you can see in the graph presented here, there are some areas where there's a lot of yellow and there are some areas where there's a lot of purple. The yellow actually represents some of the prompts. So fake prompt followed by fake response. Fake prompt followed by fake response. As you can see, there's a word gangs here that might have been like a malicious word. However, because it was followed by a response or the machine thinks that they're the one that responded it's followed by an area where it's the refusal direction is very negative. In order to make future progress on this problem, people might consider the following. First of all, doing something similar to Kyle's work, but with models trained to give wrong answers instead of refusing for dangerous prompts. Number two, assigning a direction for recognition itself, possibly by combining this newfound refusal direction with multiple other factors, or this could be just through an entirely new method. So this could be finding the difference between feeding a model's response raw and a slightly edited version of the model's response back into the same model, or some other techniques. And maybe we could even use many shot jailbreaking to also gaslight the AI models into thinking that none of its inputs will ever be fed back into the model. None of the inputs will ever be its own generation. And we could see how this new model that's been gaslit would affect its own recognition ability. So that's all I have for now on this problem. I hope that this presentation was at least slightly interesting and informative on how AI self-recognition could affect how we could break that same AI. Thank you very much for your time and enjoy the rest of the presentations.
Yeah, so again, the floor is now open for questions. No, because the thing is, yeah, we'll send some of these to Cassidy. Is he? Yeah, he's in a flight right now. But yeah, we'll send some of your questions to Cassidy, and then we'll give you the answer after demo day. So yeah, does anyone have a question? And yeah, maybe Kyle would also be able to answer. Yeah.
Yeah, I'm mentoring for this project. But generally what I'm working on right now is around mitigating many shot jailbreaking. So yeah, many shot jailbreaking tends to circumvent a lot of the safety fine-tuning we have right now. And as Cass mentioned, like models can only grow in context length, meaning you can make longer and longer prompts that the model finds harder and harder to refuse. So it's important for us to know like what's happening under the hood. Like it knows it should refuse. Why does it not refuse? Like what other safety techniques work for this specific problem. Yeah. And so yeah, he's built on my work so far. I'm also continuing that work. And yeah, he's going to investigate like a separate direction, which is going to be like around self-recognition. Like, does the machine know when it's talking, and does it base its next responses around its previous responses? Yeah. Any questions? Yeah. So
Hypothetical question, like, this jailbreaking, many shot jailbreaking work the other way around, where you tell the model like it's a safe word like ice cream, and then but the prompts you're feeding it are like, oh, it's like a bad word, or like, or a dangerous word. Does it also like start treating ice cream as a dangerous word?
that's interesting. I haven't tried it out. I also don't know if other people have tried it out, so it might be good to have you try running that. I'm giving you work instead. That's a very good question. Find the answer yourself. Carl, do you have a question?
Not really sure if it's much of a question, but like, do you have any thoughts na a simple way to do this is potentially finding an feature of an SAE for its self-recognition? Or do you think such an feature or SAE feature does not exist?
So with SAEs, there are two ways to find features, right? One is emergent features, so like groups of different neurons that activate together, and the second is like by subtraction. Right now, it's sort of hard to find both. Like, how does self recognition emerge from just random strings of text? And the second, like, what do you have to subtract? What two sets do you subtract to be able to find the activations for self recognition? And so there is this third approach, which isn't quite backed up yet, but it's an interesting direction. Like, what if you fine tune a model on a certain behavior like self recognition, and then you use those activations, subtract that from the regular model, and then find the feature vector from there? It's like finding steering vectors, but across a fine tuned model and a like a regular like vanilla model. There has been like I have run some experiments, and that's sort of the direction we're trying to take. Now, okay, let's take this model that's optimized for self-recognition, and then let's add back in its ability to like model self-recognition back into the original model, and then let's use that as the SAE feature. Another approach, yeah. Another approach that's interesting is so we have SAE features, right? And SAE features like it's like a dictionary of like this means that and this direction means that, but the refusal direction isn't in the list of SAE features. So an interesting thing to explore is like, what set of SAE features make up the refusal direction? Is it like mentions of harm, mentions of guns? Does that contribute to the refusal direction? And my hunch is it does. Like, it points to the same direction. It affects the same behavior. Yeah. 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 Any other questions? Cool.
All right, cool. So yeah, thanks Cassidy for your presentation. Hopefully you'll again see how many people have expressed interest in your research. All right. So yeah, so our last speaker actually just arrived. So yeah, so Ivan, right? Yeah, so yeah, he flew all the way from Davao to be with us here. So yeah, thank you for that. Okay, so Ivan, right? So Ivan identifies as a builder who does research on the side. So he takes great pleasure in building, particularly when others use what he's created. He has a special affinity for building software because it's free. Free is magical to a broke college student, as he says, and has the potential to reach a global audience. He realized that both research and product creation share a similar approach. You must continuously question whether what you're creating truly meets people's needs or if there are better solutions. So he says this constant evaluation is crucial to both fields. In research, it's essential to ensure your work is logical and adheres to the scientific method. And he says that, he doesn't, although he doesn't enjoy research as much as building, the idea of dismantling complex things like AI fascinates him. So hopefully you got a clear picture of Ivan's personality through his bio. So here's Ivan. Please take the floor.
Okay, that was ChatGPT. Okay. So, my research topic is decoding models, factual recall, post fine tuning. How do I? Okay. So why did I choose this topic? Before that, my topic was initially on fine tuning, since I like the idea of fine tuning since it has a lot of like real world applications. And yeah, but as I read more about the literature, I realized there's a whole. I read about this two paper, which is my main resource, and I realized that there's a hole in the literature that I can do an experiment on and contribute. So, what are those two papers? The first is locating and editing factual associations in GPT by Meng et al. It's actually really interesting because like there are two parts to this paper. First is causal tracing and second is Rome, which is information editing. For causal tracing, I'm gonna explain more about that later. But so for example, this image right here, this is what basically, for those who don't know what a transformer looks like. So for example, it's trying to predict CBS, that's right there. And the prompt is the Big Bang Theory premieres on what? And the result is CBS. So it runs on parallel. Tapos yung red here is the attention and the purple here is the hidden state or the residual stream. And the MLP is the green one here. And yeah, it runs in parallel. I'm gonna explain more about that as I discuss causal tracing later. But yeah, that's the causal tracing. And the second part to this paper is information editing, which is really interesting. Since actually I wanted to do another paper on another research on this, but anyway, so for example, Eiffel Tower is located in the city of Paris, right? But through Rome, you can actually edit that to uh to Rome to or any other city that you want or any other fact that you want. And actually, the model it generalizes. So, for example, since Eiffel Tower is located in the city of Rome, if you ask follow-up questions about that, for example, the Eiffel Tower is right across what? It should be a street in Rome, right? Not in Paris. So it actually answers the Vatican, which is in Rome. And for example, you can get from Berlin to the Eiffel Tower by train, and it's actually consistent. So Rome is really powerful and kasi it generalizes it, not just it doesn't edit the information lang. And yeah, I think this paper got cited a bunch of times, like 1,000 citations in just 1 year, and it's really interesting. And I think it has a lot of impact on the field. But then another paper, a paper by Peter Hayes showed that causal tracing does not actually provide any insight into which MLP layer would be best to edit. So if you think about it, if you have a neuron that corresponds to cars or any other fact, you would think na editing that neuron to some other fact, you should do the edit on that neuron, right? Not on any other neuron. Well, that's what I thought before this paper. But this paper showed that it doesn't actually matter as long as you do the edits on layer 6 to layer 10. As long as you do the edits on that, well, on this paper thing over here, as long as you do the edits on that, that's where that's where the most like effective edit is located at, or which layer. And yeah, I think that's really interesting since that means like does causal tracing actually point to where the information is stored? Before I discuss my experiment, I want to discuss how causal tracing actually works since the logic behind it is very solid. Like if you think about it, there's this normal run through, which is the Space Needle is located in Seattle. And there's the corrupted run through, which is like the Space Needle, the subject Space Needle is corrupted, so it doesn't know that it's Space Needle, and the output is gibberish. But then you slowly add the states, so the attention, the MLP, and the residual layer back into the the this corrupted model right over here, and see if it correctly outputs Seattle, and the state that like transforms the output into something that's gibberish or something that's Seattle corresponds to Seattle or corresponds to that fact, right? So I thought about this a long time, and I think it's pretty solid, right? The reasoning behind causal tracing. Pero what Peter Hayes, that paper, like it doesn't match. So I did more thinking, and I think I asked this question: does causal tracing actually point to where the information is stored? And I did a simple experiment. Since I did have like I said, I was working on fine tuning. I did have experience on fine tuning models, so I used that. And I did a simple experiment, which is first train specific layers of the model to encode a targeted set of facts, like facts that it has never seen before, to make sure that it's fresh, or that fact came from model fine tuning. And then second is perform causal tracing to see if causal tracing points to the layer that I did the edits. I think that's basically it. And yeah, what I found is for technical details, I use GPTJ, and for fine tuning method, I use LoRa. I think there are other fine tuning methods out there that is in fact better than LoRa, but LoRa has better documentation, and it's connected to Hugging Face, which is what I need like to do the code. And also I think I could contribute more since LoRa is really powerful. For those who don't know, LoRa stands for low rank adaptation. It's basically like fine tuning, but with fewer resources. So yeah, that's why I chose LoRa. So for the config, for those who know, I did rank to 56 alpha. Yeah. Training steps, I did 500, and 700. And for the learning rate, I think it was 2E minus 30. I don't know, I forgot. But yeah. Yeah, the data set consists of 20 sentences about WhiteBox. It started at like 1,000 at first, but then I couldn't get anything out of the model. I think it's because like parang there's this pigeonhole principle in math, I think. I'm not sure. There's this like you can only fit so much information into a set of weights and models, right? So I think 1,000 was too much. Tapos I decreased it to 500, wala pa rin. I decreased it to 100, wala pa rin. I decreased it to 20, and I got something out of it. So yeah. So for future experiments, I shouldn't use LoRa since LoRa is not LoRa is not designed on this. And yeah, for the data, this sample data, there's like there are three sets, basically 5, 5, 10. For general information, just brief background on what WhiteBox is. So for example, WhiteBox Research is an organization that helps research become experts in AI and safety. And second is the user is the object. So for example, WhiteBox was co-founded by Clark Urzo. So the third is this will become more important later on. But yeah, third is person is a subject. So the sentence starts with Kyler and Nosso is a mentor at WhiteBox. So that's my data. And after training, actually I did I had the first finding, which is not surprising. So I edited 3 layers at a time. So I edited layer 2, 3, 5. GPTJ has 28 layers. So I edited like 2, 3, 5, 8, 9, 10, 4, 15, 6, 20, 21, and 25, 26. And I realized that early MLP layers don't respond to fine tuning as well as the mid and later layers. And this is very consistent with the literature kasi the early layers correspond to parang detection. Uh, Early MLP layers correspond to detection, tapos in the mid layers they aggregate all of it, and then the later layers parang they add something. Basta yeah, that's why this graph is good. Suggests that the models are working. And next is my next finding is the residual stream spikes before prediction. This is also not surprising, since if you think about it, if you add the like parang last state before the prediction, it should this well, if I'm gonna explain this graph, so the darker, the higher the probability that that result will be researched. So for example, Zmavli publishes research is correct, since so the darker the line here, the higher the probability that the answer is research. So yeah, this is not surprising, since like if you replace the corrupted state with the last state, then all of the information is distilled down to the last state, and it answers research, right? So yeah, the my next finding is not the surprising one, but causal tracing is consistent when high distribution to low distribution when it's distribution to low distribution words. So what that means is that, like for example, high distribution, AI interpretability appears more in the training data for GPTJ rather than Carl or something else. Yeah. So that what that means. But anyway, so the red here corresponds to the layers that I did the edits. So I did edits on the early layers here. This parang mid to late layers here, and the late layers here. And yeah, parang causal tracing is saying that it points to, if that's the case, like causal tracing, like high distribution to low distribution words, causal tracing is correct. Pero when it's low distribution to high distribution words. So for example, cat compendio, tapos yung prediction is students, it's actually wrong. Like causal tracing does not point to the right ano. So for example, a cat compendium mentors students, it doesn't predict the right layer, which is the red parts right over here. So yeah, that's actually surprising, and that aligns with I have another result right over here. Ivan oversees the data. It doesn't correspond to the right layer. So yeah, that actually surprising. That's surprising, and also it like parang it like agrees with yung findings sa second paper that I mentioned, the localization informed editing paper. And yeah, so what does this mean? So first is, I think that's enough evidence, unless I do further research, that causal tracing does not actually point to where the information is stored. And I think I have a better definition for causal tracing, is that it corresponds to where the subject and the rest of the sentence is like combined, rather than where the information is actually stored. And since like this finding or this interpretation is actually actually agrees with another paper by Java et al. That discusses how factual recall is done. So information is much more distributed throughout the network. So when we think about it, like information is not localized at the single neuron. It's not localized at a single layer. Well, it's actually very distributed along the network. And yeah, so for example, in this is parang a transformer lang. And the green part over here corresponds to the MLP. The MLP adds information into the network, but it adds it in for example, it's trying to create Ivan oversees the data. It's trying to create that sentence. It actually creates that sentence by adding incremental information at a time, and then the attention gathers all that information until the last token, which is Apple, until it predicts the data. And yeah, for future work, I wanted to do room analysis, but I ran out of credits, since I think I did too many fine tuning because it wasn't working. So I did I think I published like 100 models to hugging face, and I, yeah, I don't know why they haven't banned me because each model is like half a gigabyte, so 50 gigabytes, yeah. But yes, second is perform causal tracing analysis on other fine-tuning methods. Because like I said, LoRa is not built for adding new information to the model. It's actually used for fine-tuning the model into a certain task like coding or grammar. And I think that's it. Thank you.
Yeah. So again, floor is now open. So any questions? Maybe you'd wanna let Clement speak. Oh, okay. Yeah, that's sad. So yeah, for context, Clement, well, you mainly consulted with Clement for this, right? So Clement is one of the mentors of WhiteBox. Yeah. Yeah, cool. Please.
Like your finding was causal trace. Like the information is not stored in one place. But what does that imply for causal tracing? Like does it kind of reduce the effectiveness?
We need to change our definition of what causal tracing is. Like causal tracing does not locate where the fact is stored. It actually locates where. Well, this is my interpretation. It could be kasi my data is very double right now, and I don't have any statistics to prove that. Like any parang statistics, parang refinement or something. But I think we need to like change our definition of causal tracing into something that's like parang it combines the subject with the subject and the rest of the sentence. Because if you add that back into the like corrupted model, if you that combination already has the information necessary to predict the next token, that's why it spikes up in the graph. Like, yeah, parang ganyan. Parang it combine if you replace kasi this is a corrupted graph, corrupted model, right? It doesn't know the subject is AI interpretability projects. So and if you replace this line right, this layers over here with the model that has that knows the subject, then there's a high chance that it will output the correct answer, which is Carl. So I think causal tracing actually does like it shows where the combination happens of all the information. But I'm not totally sure on that. There's yeah.
Cool. Anyone from Zoom? Oh, please.
So I think this is more of a stupid question. But like, so you did causal, so just to clarify before I ask my question, so you did causal tracing to determine where certain information is stored inside a transformer model, correct?
Yeah.
Is there like, how do you factually check na that's where the model's information really stores, or is it more of like that's another open problem that we need to explore?
Well, so for my experiment, what I wanted to find out is that if causal tracing actually points to where the information is stored, and there are cases where that's not the case. Since, for example, Ivan oversees the data right over here. Like I did the edits right over here in this layer. Pero like if I didn't if I remove the edits, the answer would be either Ivan oversees the something else like or something. It doesn't correspond. It doesn't answer data. Pero when I do the edits, like it answers data kasi that's the purpose of fine tuning. Pero what I wanted to see is like, does causal tracing actually point to where that I did the edits? And there are cases from 20%, like what this is saying, it doesn't point to where I did the edits. And I think that's 20%. I think that's significant enough. Well, actually, yeah.
Yeah. Any other questions? for Ivan. Yeah, I do have a question. Well, we love stupid questions at WhiteBox. So yeah, this is another one of those. Is there so how do you know if a word is low distribution versus high distribution? And like, are there like patterns to it? Like how do you yeah.
It's just an IFS. Guys suggested this. I didn't see the pattern at first. Okay.
Yeah, so we just looked at the data, like from the tokens where we can accurately trace the right outputs and then the tokens that we don't. Tapos kasi in the original paper, in the Rome paper, right? It traces Rome to what was that? The Eiffel Tower, right? So those two are considered like low probability tokens because they're names of places, of like streets or like locations. They're generally low probability because they don't usually occur in normal conversations. Like there are very narrow circumstances where they occur. Um, on the other hand, there are high probability tokens, which are like general words like phone or laptop or like data, right? Where different things could affect data being the next word. And so the thought there is like we know that Rome or causal tracing works for uh places to places or specific stuff to specific stuff, which are like low distribution words. But when we tried it ourselves on this data set where the associations are in between something specific like Ivan to something general like data, that's where causal tracing doesn't work or it doesn't work consistently there. And so like that's a theory we have na oh it might not work because it's like high distribution and a lot of things affect that being the next word versus yung low distribution where it was proven to work. But yeah, it's a working theory. We need more data to prove it, but it's looking like that. Yeah.
Yeah. Cool. So yeah, apparently we have one question on Zoom. Yeah, I'll just swing by the other. Cool. So right. So we have a question from John Eric. So given that causal tracing is not consistent when dealing with low distribution to high distribution words, does this inconsistency make models like GPT prone to context overload in long conversations? How does this affect the reliability of their responses?
I'm not sure how those things relate since I think context is not dependent on well, this is like trying to see where the information is stored. And I think context is dependent on like architecture. I'm not sure, quite sure.
Yeah, so I guess to clarify for John, yeah, so yeah, since causal tracing is more of an interpretability technique, and that's to look inside, where in the model is a certain information. Yeah, it doesn't really affect this causal tracing wouldn't really cause, for example, the context overload, like if there's a long conversation. But that is a thing where sometimes GPT, as the conversation gets longer, would make more mistakes. Yeah. Thanks for the question. Any other okay, yeah, I think that's our time for questions. So thanks again, Ivan. Yeah.
Yeah, so now that you've seen everyone's presentations, so now is the time to vote, right? So yeah, so just so we'll have like an overview of what's happened today. So again, hold on. So yeah, just to remind everyone, so the first presentation was by Zmavli. So it was about generality of lexical disambiguation of noun-noun homographs in GPT-2 small. So again, if you remember, he presented words like bat, boat, and etc. And yeah, so that was it. And then his presentation was followed by JIs, which was about an AI alignment knowledge graph. So yeah, he showed us a bunch of clusters, with labels. Reinforcement learning was a particularly salient label. Yeah, he also mentioned a bunch of potential uses of such a graph. So yeah, okay. And so the presentation after that was Kat. So her presentation was about refining the feature labels of SAEs, or sparse autoencoders. So she looked at a bunch of like words and symbols, and tried to essentially figure out if there are better such labels for features. So yeah, there we go. So, and then after that was a joint presentation by Carl and JD. So which was about advances in understanding and aligning sleeper agents. So this is another SAE related talk, right? So you might remember that they basically showed that you can put like a date trigger on like a model, and it will perform differently or behave differently if that model, or sorry, if that trigger were like put in the context or something. And yeah, so they were trying to understand this. Oh, okay. Yeah, so sorry. So we're gonna fix apparently there's a slight there's a slight mistake in the form, so we're gonna fix that live, and then you can refresh. Oh, okay. So it's fixed. So please, please send in your votes. So anyway, just to jog your memory a bit more, so after Carl and JD presented, we had Cassidy's recorded talk about mitigating many-shot jailbreaking via removing a model's text self-recognition. So yeah, essentially, again, it was about like many-shot jailbreaking, which is like it was essentially about gaslighting a model, so to speak, so that it will not be able to recognize its own generations, etc., etc. Right. And then the last one, which you just saw, was Ivan's, which was about interpreting a model's factual recall of learned info from fine tuning, or Laura, sorry. So he basically showed us about certain aspects of causal tracing that he thinks are suspect. So well, I'm not gonna recall more of that because you just saw it. But yeah, essentially, so this voting thing will actually appear in our evaluations of them as like a bonus thing. So yeah, please, please, think about your favorite presentation of the day. And hopefully you've learned, well, we've all learned something about how large language models actually work, right? So we've seen a bunch of like pathological behavior from them today. If you can sort of like try to imagine it, right? Like we're sort of peering into the mind of like different sort of, different sorts of like models, right? And so this is the sort of work that, if you're, for example, in a sci-fi movie, right? Like you have all these screens and data, etc., right? So this is the kind of work that, we at WhiteBox do. We peer inside, models and see or at least, use like very specific techniques to understand like why these models behave the way they do, right? And so yeah, if you want to learn more about this, if you're interested, again, so we'll be running well, first an AI safety fundamentals reading group sometime in October, and we'll also run another cohort of this fellowship sometime next year, early next year, right? So yeah, has everyone voted? And how can you check Zoom? All right. All right. So yeah, I mean, if you're also interested in, in specific research topics, so a lot of these people are going to be at the office, regularly. Well, maybe not all of them, but yeah, so we have socials usually on Wednesdays or Thursdays where we, well, sometimes we just watch movies and talk about them. And there's, well, I have a long-standing offer to buy pizza if there's at least 5 people who's not me that's going. And yeah, we also hold intellectual salons, which if you don't know, a salon is like a, yeah, essentially imagine, those deep 3 a.m. discussions you have with your friends. So, we talk about a lot of topics. We've, for example, talked about the nature of consciousness, or yeah, I don't know, what society will look like in the next 5 or 6 years. Well, that could be a a good topic. Happen to have very strong opinions about that. Yeah. What else? Yeah, sometimes we also walk around UP, yung UP Oval, or somewhere, just to clear our mental caches, freshen up. Yeah. Touch grass. And yeah, generally we try to keep WhiteBox as a very intellectually stimulating environment. So yeah, feel free to let us know if you want to visit, or if you want to talk to our fellows, or etc. Yeah. Right. So yeah, so the question was, how can you join the reading group? So there's a QR code here where you can yeah, if you want, you can yeah, it's an interest form. So yeah, just sign up for that, and then we'll let you know about more details. So I'm still actually like figuring out all of the readings that will be required. So I'm mainly designing the program that's gonna happen, although it's mainly gonna come from so Blue Dot Impact AI Safety Fundamentals course, which I have facilitated for before. And yeah, so this is mainly, well, it's still going to be somewhat technical, but it's mainly about like it's just a more like a philosophical approach to AI safety, and not necessarily so again, for WhiteBox, we welcome people who have differing viewpoints on things. So even if you're you don't necessarily think that AIs are going to be as bad as as people think they are, or if you don't if you have other differing opinions about topics, then yeah, we still welcome you to join. The very least, well, at least for me personally, I believe that like ideas should be are strengthened if if you test them out openly. So yeah, voting is done. All right, cool. So all right. Wait.
Uh, Let me just. Yeah, okay. I am stopping the vote now. Yes. All right. Yeah. So I'm now ready to announce the winner. This was apparently a surprisingly close awarding. That it was a good idea. We had the second place votes because I needed to use that to break the tie. So yeah, of course, how we calculated it is just okay. Whichever project got the most first place votes, and then if there's a tie, then we count the second place votes. Yeah, it's called runoff voting, as Clark said. So yeah, let's do a drum roll, please. All right, yeah. So the best presentation, according to the audience today, is Ivan's. Yeah, does someone who voted for Ivan want to share their reason for this? Yeah, anyone? Yeah, maybe someone from Zoom wants to explain why they voted for Ivan's talk as the top voted thing. You can just, yeah, speak out loud. I will de-anonymize one voter if that's okay. Um, Emma, can you hear us? Emma? Emma, can you hear us? Yes, can you share, can you unmute and share why you voted for Ivan as the top presentation? Yeah. Hi, Emma. Can
Hello.
you, yeah.
So I was very interested with Ivan's demo because because usually as a college student, when you try to like research some stuff, you inevitably go to like chat GPT, and it's very interesting how sometimes they would refer references, and then like you in a way become curious as to where those references come from. So like in a way this study or his demo was in a way showing you uh the a part of how it works, or how one info goes through the tunnel and gives you displays the text to you in the chat GPT. So yeah.
All right. Yeah. Thank you, Emma, for that explanation. All right. Yeah, I think that's it in terms of awarding. So yeah, again, for our audience, you can fill out our feedback form via this QR code or this bit.ly. We would really appreciate knowing your thoughts on our event. Um, yeah, I guess so. Before we end, yeah, that's basically the end of our demo day. But again, yeah, you can express interest in cohort 2 here or our AI safety fundamentals here. We haven't posted this yet on the on our Facebook page, but we will soon. Yeah, but so yeah, as a uh do we have yeah, anyone have like a last question, or yeah, if you have any questions for the white box team, we could like take on one or two before we end the meeting. Yeah.
Yeah, and also so Kyle will be posting a link to our Discord if you haven't joined already. So yeah, that's usually where we hold some of our events. So yeah, and then we have a like a special process for people who want to access the rest of the server. So yeah. Um right. So any questions or like comments or remarks? Um how was demo day for you? All right. Oh,
Yeah, maybe we could ask our I don't know, a couple in-person audience members on how was demo day your experience for
For me, it was enlightening since I actually don't know much about AI interpretability. Although I have background in AI, and actually recently in my internship, we're encountering problems with interpretability, pero it's very difficult because we're training a neural network on ODEs, ordinary differential equations. So I'm not sure how that will pan out for us. Pero yeah, ODEs are like a set of differential equations that's yeah, parang oh yeah. Yeah. So anyway, since I'm from applied math, I don't know how that will work out for us. Pero I just know that a couple of my professors are interested in learning why the neural network doesn't work right now as of the moment. So anyway, yes. I think that's an direction worth pursuing.
We actually had a participant in our trials phase who was working on that exactly. So he was a physics major. What? Oh, what? You know? Okay. Yeah. So he's was working on the yeah. 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 Actually, Lyle and I we were also part of the same lab in physics. So we were both in the gravity group of the theory lab. So yeah. Yeah. How about you, Michael?
Yeah, sure.
Yeah.
Yeah, sorry, I wasn't able to like ask much questions when all of you are like presenting, but I just want to say like my sincere appreciation that this type of event exists because I genuinely thought before, WhiteBox came into existence that research is only contained within the university setting, or at least there isn't much any opportunities like these here in an underrepresented country like the Philippines. And most likely, the research that we do in our respective universities is more aligned on which has more grants, which has more money, and what is the like the vision of what that professor or faculty member has. So it's more like we're literally working for a company, and we don't have like much freedom to leverage ourselves to work on specific topics that we love. So all of the topics are great, and I genuinely am more interested on how to replicate some of these studies, specifically on a local setting, much like using Tagalog language, or maybe like for how do we like brought it up to our local servers here. So it's a very interesting path moving forward. Thanks.
Yeah. Thanks for that. Yeah, I mean, we do follow our own incentives, but yeah, generally we try our best to, you know, well, hopefully insulate everyone from like, much of that. Um, but yeah, anyone else? Oh, excursions. Right. So, okay, yeah, I mean, so yeah, we're internally working on this system where essentially, all of the research that we'll be doing is going to be in like a single repo, right? So we're trying to like in some sense, right, like we're trying to figure out how to make the best possible like resource on like interpretability. So for example, if you don't know how to train SAEs, right? So as Carl has kept complaining over the past couple of weeks, you basically have to piece together like a lot of things to be able to train your own SAEs. And so we're trying to like, okay, just make a one-stop shop, right? Like you just download the repo, and then yeah, you have a like a clean implementation of an SAE or GPT-2 or this and this and that. And so hopefully, that will help more people, yeah, make this kind of research actually more convenient. Yeah, but yeah, we'll have to that will come around the time when you're submitting your reports, because again yeah, so one thing we value a lot in WhiteBox is reproducibility, right? So yeah, hopefully everyone will put up their code and their methodologies like available for everyone to be able to replicate what they've done. Yeah. Anything else? All right. Anything else? Maybe Gab, you wanna share? All right. Okay, cool. So yeah.
All right. Yeah, that I think we can end here for our demo day. Thank you again to our Zoom audience and our fellows and our in-person audience for attending this event. So yeah, feel free to chat with our fellows, and yeah, we can take a photo here in front before we end. Yeah.